a bit of a reality inversion. I'm talking about changing our scale of thinking in terms of geophysics from meters and kilometers to meters to centimeters. And we're using EM to help quantify some constraints to crop growth in the lower Ganges floodplain in India and West Bengal. West Bengal and Bangladesh. It's right. The project is called Supporting Cropping Systems Intensification in the Salt-Affected Coastal Zone of Bangladesh and West Bengal. It's funded by the Australian Centre for International and Agricultural Research. Just some background features of the study area. We get about between 1,500 and 3,000 millimetres of rain each year. And with every wet season, about 2/3 of Bangladesh goes underwater and the whole lot of West Bengal. Our study area is all within about 5 metres of sea level. And the salinity of river water in this situation is highly temporal through the season as well. So with all the rain in the wet season, the fresh water blasts through the system and you have this big plume of fresh water going out in the Bay of Bengal. And slowly as those rivers dry up of their snow melt water up in the Himalayas, the seawater starts coming back up the streams and back into our soil environment. So we have temporal effect of salinity on our crops, and that has a huge impact. And so this marching of the seawater back up the rivers changes our soil salinity from less than 1 decisemen up to 4 decisemen, which pretty much kill any crop. Not in every area, but this is the serious end of the debate. So what is the problem? Well, besides the fact we have a massive population that need to improve their livelihoods and improve their food security, we've got the temporal salinity, which really inhibits our capacity to interpret cropping trials. Now, our job in this project is to try and get or increase the agricultural production by growing shorter season varieties, having early sowing dates so you can get an extra crop into the rotation. So mostly in these systems we have a rice crop on the back of the wet season just about everywhere in this zone. After that crop is harvested, they'll put in another crop. It might be rice, it might be vegetables. There's a whole range of different cropping scenarios for that second crop, and there's even a third crop in some areas that they can get away with. Now, if we can introduce varieties that can be sown earlier, that can be harvested earlier, and whatever else, we might be able to sneak another crop into that rotation, and that has a huge impact for everyone involved. So we're attempting to use EM to help solve this problem of the temporal variability of salinity, and we're using the EM response as a covariate to those cropping trials. So we have a whole bunch of trial plots growing a whole bunch of different varieties to meet that need, and we're trying to use the apparent conductivity as another vector in that analysis. Oops. This slide gives you a bit of an idea of what's happening. I borrowed an EM38 to do an EM survey over. This is a maize trial that you can see here. That's the salinity or the conductance in the top 0.75 of a metre depth of inquiry, and that's a gross conductance over that depth. And you can see that the ore body halide what's the other one? Halite gypsum ore body is there, and there'll be a fair bit of water and salt as well contributing to that signal. And you can see down here, this is an aerial view of the same trial. You can see the salinity affected plots in that area. So this gave us the idea that we probably should be trying to use EM in this environment. So we went off and bought that the other instrument that was on that first slide. I can just go back. Whoops. This instrument here is a dual EM1SH. It's very similar to an EM38, except that it has 4 coil separations, giving us 4 effective depths of inquiry within the root zone, the top 1.5 meters. And this is some raw data from Gasaba Island in West Bengal. The points here are points taken on individual trial plots, like you saw on that previous slide. I can't remember what the crop was in this instance, but these are the raw values from each of our coil separations. It's fairly dead here in the 0.3 meter coil separation. Salinity starting to build at 0.5, 0.8, and this is 1.6 meters of depth. Just our feature here, we've got a bit of a high conductor up the end there, and there's actually a road that goes through there, which is essentially a bund. Because this country's always underwater, all the roads are up 2 meters off the land surface to account for that. So essentially there's a big dam bank there and the water accumulates at that point, and that's why we've got high conductance. Where there's water, there's salt, essentially. This is another survey sorry, let's go back. This is 5 second data. So the instrument's put on the ground. It's left to average over 5 seconds. I think it accumulates data at 1/10 of a second. So it averages data over 5 seconds and saves the output. In this scenario, this is 1 second data, and this is with the instrument carried along on the go. The instrument has an inbuilt GPS as well, and that's all stamped in with the data. So this walking survey was conducted. You can see where we walked for this one, and actually that slide I showed you before, that red loop is actually part of that larger survey area. Again, you can see it's pretty dead in the top 0.3 coil, starting to build at 0.5 meter, starting to build at 0.8, and then when we get down to 1.6, we're starting to see a lot more conductance come through. To interpret this one, I said before there was a bit of a conductor up the top there, and that's correct. So that road goes through there. To interpret what's going on down here, you can see there's a gap in the data there, and that comes through in each. It's just creaked across that gap. But the reason there's a gap there is because it's a farm storage dam. And you can see on the western side there's a bit of a plume coming up on the western side of that dam, which I think relates to water leaking out of that dam or the overflow path of that dam when it fills and runs off. Down here in the bottom corner, there's another dam down there as well, and that's contributing to our conductance. That's my interpretation of what's happening. So we decided to buy some inversion software to help us try and change those conductivity depth intervals into actual slices, or CDIs they call them. And when we look at, this is the Gasaba Island example, and that red loop is that original survey that I showed. And these are what the depth slices look like as we go down. So what is it that I'm struggling with? I've got lots of pretty pictures. They show me a bit about the conductance. the problem I'm having is that the field measurements that I take in these trial points, so we do soil sample holes at an even conductivity space throughout that crop trial. So we just rank the conductances and break it in. We think we've got time to dig 10 sample holes. We'll break it into 10 even conductivity bands, pick those points, and then go and sample those points for one of the coil separations. That's how we sample. And then we take those back to the lab and do 1 to 5 and soil moisture measurements, EC measurements, that is. But I've had trouble trying to match the laboratory data to the actual conductance and to the inverted data as well. I'm not quite sure yet whether I've got the right laboratory technique for doing this, and that's one of the big questions. Should I be doing saturation extracts as opposed to 1 part soil and 5 parts water? A couple of other points. I feel the EM results are pretty good. They're a bit light on in the top coil separation. That's possibly because the soil water's been extracted by the plants. It's pretty dry and pretty dead up there, and we're not getting much response, which is probably okay. It's probably real. But I think I probably need to go back and have a look at some of the first principles that we looked at yesterday and look at some of the things like skin effect, that type of thing. I think the whole project needs a bit of an overhaul in survey design. I think I need to tighten up on our positions where we sample and line up the crop trial spacing based on either a 3D grid or a 2D transect type geometry to try and help with that. One thing that keeps me awake at night a little bit, this is the R squared of this is measured data versus modeled data, and these values here that come off the 1-to-1 fit all come from the one coil, and I'm concerned that I need to amp up the conductance in that coil to bring that line up there. But I need to talk to the company about that. Another question I've just got for everyone is, do you think that I'm pushing this sort of technology beyond what it might be likely to tell me? And essentially, that's it. Questions?
What sort of frequencies are your coils using?
It's set frequency 10 hertz.
Pardon me?
10.
But it must have different frequencies for different coils, do you?
No, same. Set frequency. It's got one transmitter and 4 receiver loops. 10 kilohertz, sorry, 10 kilohertz.
What's your coil separation?
There's one coil separation at 0.5 meter and another at 1 meter, but we have 2 at each of those positions. We have a coil in the opposite orientation to the transmitter and in parallel to the transmitter, and when you do the maths, it gives you the different depths of inquiry, as I've said.
So they're not at a fixed, so the 4 coils aren't at a fixed separation from each other?
Yeah, they're fixed.
I would admit that it's not 0.5 meter between each of the 4.
No, the whole thing is about 1 meter long. There's a coil at 0.5 meter, another one just behind it in the opposite orientation, and the same at 1 meter.
So you have to do a lot of splades, I guess, a lot of transects. Narrows and stuff.
For 3D, yeah. So in that example where we did the walking survey, I just got a handheld GPS and got the crew to just try and fit it in. It was only, what can you do in 2 hours? So you just think, yeah. And the thing is, like, we bought this instrument. I had 4 days to play with it before taking it to Bangladesh. And then I had another 4 days to try and train up my crew over there on how to use it. I didn't even know how to use it at that point. And, you know, after a while we got them going, they were collecting data. That was all good. But, you know, I've got a long way to go. I've got more training to prepare for these guys. When I went and collected the data, I didn't have any inversion software, so I didn't know really what the geometry should be or, you know, how that impacts, but I've got more of an idea now, so I can tighten some of that up.
This in for soil, does it only invert quadrature, or is it a full quadrature in phase inversion that will take into account of that part where the in phase drops back off?
I'd have to have a look, David. The software has a pick list of a whole bunch of different instruments that it'll invert. It has mine on the list, but there's a whole bunch of Geonics equipment in there, and Julian.
Yeah, the trouble is, the Geonics instrument takes an assumption that quadrature is a straight line and just kicks the conductivity off that. In fact, it tapers off. The in phase one pops back down.
Yes.
It's the other way around. It's the other way around, isn't it?
I think I know where you're going with this. It works on the theory that at low induction numbers, 70% of the conductance is for those effective depths that I've said with that geometry. That's the theory. Now, if you go, and there's thresholds in the manual that say if you have conductances that exceed, I don't know, 250, I think is the lowest on one of the coil separations. If you exceed 250, you're better off converting the in phase back to use that value once you exceed, because you're above low inductance.
So your software package may not be using that. It might just be taking this low induction number in assumption in.
It may, but I don't have a hell of a lot of ground that's above those thresholds. So I know the graph went up to 600, but I think it's the 50 centimeter coil that's got the lowest threshold for conductance in that sense. But you're right, I should look at it.
Do you actually get out two numbers then for each of the receivers?
Yes, you get.
They give you an in-phase and quadrature.
They give you both. Yeah.
Okay, that's good. The other thing you'd mentioned that you need to look at things like skin depth.
Yes.
That's probably not, given that you have kind of low conductance values here, it's probably not a big issue. If you look at these, there's this a typical curve that kind of goes with these horizontal loop systems, so that the response is like a characteristic curve that is the same for a normalized depth, where it's the true depth divided by your coil separation, and then there's a peak in there which kind of tells you what your maximum, where you're most sensitive to. So these are things that kind of then help you understand like how I'm going from the type curve of that instrument down to successive greater depths of penetration. And then the fundamental assumption for using the quadrature component is just that the skin depth that you got has to be much greater than your separation of the coils.
Right.
So long as the skin depth is greater than the separation of the coils, then the number that you're going to get out is actually pretty good for using that quadrature and getting out an apparent resistivity.
Okay, well, let's say the skin depth is 30 centimeters and the coil separation is 50.
Yeah, so now you're violating
that threshold.
Now you would need to be actually working with both the in-phase and the quadrature to kind of see what kind of conductivity I've got.
Okay, that's fantastic advice. Thank you. Okay.
Any volunteers to go back? The last one. So this will get you back. Cool. And that's
worries. So this is a case study I was working on a few months ago at Karambarini within the Batten Fault Zone in the MacArthur Basin. So this area is about 10 kilometres north of the MacArthur River mine. And so what we had over this area is as part of the project we're working on, we got some 500 metre spaced ground gravity data acquired over this area, and we had some VTEM data that was collected, I think, in 2009, which some of my colleagues at SARA have reinverted. So we've basically taken the interpretation from the gravity data. I did some gravity modelling and compared that to the interpretation of the newly inverted EM data. And so the first thing that I did here was basically look at the gravity, the AEM, and the radiometrics to produce a solid geological map of the area. So it's not very deep, but there's a tiny bit of cover. So we had some outcrop. There was a bit of existing mapping that NTEGS did. So I basically interpreted the gravity and the AEM data to come up with this map, and also interpret a lot of the faults that are found at the surface that you're not seeing in, particularly the mag data is not particularly useful in this area. Sediments have very low magnetic susceptibility, so all you're seeing is the basement within the magnetic data. But the gravity data came out really well, especially if you look at the vertical derivative here. We're almost picking out the geology at the formation scale within the gravity data. So you've got these gravity highs and low, which corresponds to different formations that we've mapped there. When we're picking out in the AEM data a few faults that also correlate with the edge of this gravity high that we're seeing. So this data is located along the EMU fault. It's a major north-south structure within the Batten Fault Zone, and we see that in the gravity data, the radiometrics, AEM, and even at a larger scale in the mag data. So going into this project, we were given a 3D implicit model that was built a few years ago based on some structural data and some drill hole constraints. And I've taken that data and used it to constrain the gravity model. And basically all I did here was take the existing model and find out where the problems were. So I broke it down into the stratigraphic layers that we have. We got quite good control on the densities. There's a lot of rock property measurements throughout the whole sequence of the MacArthur Basin, so we had a lot of control of that. What I've done is taken this model, populated it with the density measurements, inverted it, and what we see in this one particular layer where we're getting all these density anomalies stand out, that was telling me that there was a structural problem with that part of the model. So look at that. So I looked at where we're getting these density anomalies within the model and compared it with the geological map. What we're seeing is it's sort of confined within this area west of the EMU fault and bound by this fault that we're picking up in the EM data. And so I came up with a few possible interpretations as to why we're seeing this density anomaly. It could be that we're getting sediments thickening towards the EMU fault. If we have a thicker, denser layer there, then that anomaly would disappear within the inversion. It could be that it's at a reverse fault, it's been that unit's actually shallower than what we've initially modelled, or we could have a sub-basin adjacent to the EMU fault. So elsewhere along the strike of the EMU fault, you do see thickening of sediments, especially the Barney Creek Formation, which is what we're trying to interpret. It was the end goal of this work, is trying to pick up the Barney Creek Formation, which is what hosts the MacArthur River deposit. So we came up with a couple of possible interpretations there. And then we looked at the AEM data. So just some guys at SARA just re-inverted this. And this is just a couple of sections that we had. So we have a drill hole through this here, and the Barney Creek Formation is, we know it's quite conductive. And the marker from the drill hole actually intersects this conductor here. So we know here, we've got control on that, we know that's Bunny Creek Formation. The problem is, as we come along this section, then the AEM data splits into these two conductors, and we don't know here if it's the deeper one or if it's the shallow one. If this is another formation coming in, or if we got a fault, this could be a sub-basin along here. So this is a problem we're having. Hopefully in the next few months there'll be some bit of drilling out there. We'll have a few more constraints, and then we can come back and update this model. But what we did is we basically came up with two interpretations of this, of the deep and shallow conductor, and also compared that to where we're seeing the density anomalies. So this is just a section through that what we modeled as a reward dollar stone, where we're getting this density anomaly, comparing that to the interpretation of the deep and shallow conductor. So this is just showing the depth to the top of the conductive anomaly there. So this is, at the end of the day, this is our preferred model, because the deep conductor is actually getting quite close to the depth of investigation. We don't have a lot of confidence in that interpretation, but we're seeing this increase in depth to the top of the Bunny Creek Formation here. It correlates well with the density anomaly that we're seeing in the gravity inversions. So we've got these two new surfaces that we then put into a new 3D model, then re-inverted that against the gravity data. We're getting, actually both models produce a much better fit to the gravity data. So again, both could be plausible, but this is our preferred model. And it also fits better with the geological data we have. So what we thought this could be is a sub-basin adjacent to the EMU fault. So a transtensional sub-basin is what we're seeing elsewhere along the EMU fault as well. So we came up with a geological model. So you've got these transtensional sub-basins. Again, this is another one of these sub-basins that you're seeing further to the south within the Batten Fault Zone. So this is a sort of evolving model at the moment. We're still collecting a bit more geological data, and hopefully there'll be a bit of drilling in the next few months, and we'll be able to look at that data and just continually update this model. I think that's it. Thank you.
I really like these, what do you call it, collaborative inversion approaches, where you use output of one geophysical method to help constrain the other. It's a really powerful tool. Have you considered simultaneously jointly inverting these data sets?
No, that's not something I know how to do. I don't know if people have tried before, or if there's software out there to do that. I'm sure there probably is.
Yeah, so at least I know Schlumberger has made some headway in this. I think the oil industry has, but I think there's a few people dabbling with it at GA.
Yeah.
I have some good input on that.
Definitely be powerful. Yeah. Thanks.
Hello, everybody. My name is Qiu Yan, a PhD student, and my research focus is three-dimensional time domain airborne electromagnetic modeling and inversion. So it sounds much more theoretical, so maybe a little boring, but I will go faster. And today, I'm very happy having this chance to share some of my research work with all of you. So maybe if possible, you can give me some suggestions for my study research work. Okay. So, as we all know, no matter for the semi-airborne survey or airborne surveys, they all produce large amounts of data. So in the past, for 3D calculation, the time and the memory cost are almost unpractical. So conventionally, the imaging and 1D inversion are the best choice. But in recent years, many acceleration techniques have been proposed. I think there are two main methods. The first one is the direct solver used in EM calculation presented by Professor Duck, and another one is the moving footprint proposed by Professor Leif Cox. To further speed up my 3D calculation, I adopt the field separation method. Here, I use a half-space or layered Earth in time domain response as the primary field, and the normally target response as the secondary field. So we can get the response where solving the second field equation. This method has several advantages. The first one is the secondary field footprint is much smaller than the transmitter footprint. It means I can do the calculation in a much smaller area. It means less grids, less time cost. And the second one is I don't need to consider any singularity problems or the field fast change around the transmitters, because I calculate the primary field via a semi-analytical solution. And the third one is the primary field can be stored in memory for reviews. Except this method, I also adopt the local mesh to further decrease the grid number. The local mesh means has fine cells in the center and close ones far away. And additionally, the direct solver is used to solve this time domain equation. So I combine all these merits of these methods together to conduct a faster three-dimensional calculation. And now I will show one example. This is the model, and this is the profile response. The diamonds are the separation method results, and the solid line is the total field method. Here, the total field method means I directly calculate the response without any field separation, and the transmitting current is directly put in the transmitter loop and then do the calculation. So I compare the speed, and this we can see the field separation method is much faster than the total field method, and the total time is about 75% less. It means if this method costs 1 hour, maybe the field separation method just needs 15 minutes. And I also do the before.
Can you go back to that?
Yeah.
So
yeah.
who was who? Yeah. So this first, that first picture. What is? Yeah.
This one?
No, you're okay. Next slide.
Next slide.
Yeah. So I'm curious about this dip at early times. Is that? Yeah, your early time channels.
Early time channels.
Yes. So there's a negative that's going on.
This is step waveform. This is d beta dt. So they should be negative and then positive. But for the B field, it should be positive. Okay. Sorry, it can't see that. So this is the step transmitting waveform. So I calculate the half-sine transmitting waveform, and this is the response. We can see on-time signal there is sign change. What's interesting is the sign changing place is corresponding to the edge of this target. It's 200 meters. It's 200 meters. But the off-time signal is much smoother. So maybe I should do some more research work on time data. So above all is my 3D modeling. So based on the modeling work, I have done the inversion. But I think the time should be 5 minutes, so I just show one result. this is the lesion zone, and this is the massive sulfate. I used 4 lines to invert this data, and this is just a section to fit this drill hole section. So I think maybe the shape, the depth and the shape and the resistivity almost being inverted. Okay, all the above is some of my research work. Thank you for listening. Thanks.
Awesome. Okay. Okay, that's okay. Okay. Yes, thank you. Today I will be talking about a slightly different topic about the geomagnetic industrial patterns in Australia. So all my talk, this has been published in Space Weather in December 2016. If not clear, you can have a read my paper. So in Australia, we have a fully connected electrical grid in the east and the west coast. Also, we have a significant pipeline network shown on those left. So it's important to understanding the geomagnetic induced current because as a consequence of our power problem could be a significant. So it's all well known that geomagnetic GeoSci study will be usually divided into 2 steps. It's a geophysical step and the engineering step. So today I'll be just talk about the geophysical step. So the data we are using is called Australia-wide array of geomagnetic stations. The spacing size about 275 kilometers. So a broad scale 3D electrical conductivity model was derived from this data set. The data was collected in early 1990. So here I highlight a few conductivity map at different depths. The first one, this figure shows the cluster elements between the two major Australia cratons, northwestern and north and Central Australia craton, and this figure highlights there's a significant electrical conductivity contrast in the Arctic craton in the Western Australia, and the third figure shows that there's say about 5, the conductive region at the 325 kilometers is a be in the mantle depth. Okay, so now we're using the 3D model to address the geomagnetic induced hazards. First one is a simple 2-layer model with no reference to the conductivity contrast between land and ocean. Of course, the induced field is a uniform across the continent. Okay, this model is called ocean and continent model. This model accounts for the conductivity contrast between the land and the ocean, and no reference any the conductivity anomaly on the land. So we can see in the Central Australia here is a pretty much like the simple model we saw in the previous slides, but there's a enhancement in the fields here, and also distortion in the direction of a telluric vector somewhere here. So there's next we have a progress into the full 3D electrical conductivity model, as I show the 3 depths in the second slide. You can see in the West Australia, like here, the distortion, the electrical currents could be double compared in the other place. Okay, this is the slides. Okay, now we are using the model we have tried derived induced electrical currents. First, what we are doing is we have a measure magnetic fields and electrical fields in the central Australia in the Alice Springs Geomagnetic Observatory, and we calculate the response tensor, just like an impedance tensor. Then we recalculate from the impedance tensor and the magnetic fields, we recalculate the time series of electrical fields. You can see this is different between the estimated with the measured. Certainly, they are very good because we are calculated from the measure. Okay, now we are using the conductivity model to calculate the response function as you show the dot points on the right panel. And because the conductivity model do not a very good resolution at the shallow depths, so we have some limited the bandwidth only to here. And also, as you say, that we are predict red and measure the black. There's some difference, especially during the rapid magnetic variation, large difference. This is because the response function short of the lack of the short period data in there. Okay. So this probably you'll see is a Jingling's figure. So now so this image show that have a proposed and in progress and complete OSDAM program station. So once those OSDAM data become available, and we have a far more detailed electrical conductivity can be derived, and that model can be used for the GRC study in Australia. That's it. And also the electrical conductivity model published in the Geophysical Journal International. So if you want to look at the model, it's there.
Great. Nice. Thanks.
So there's another presentation on the FDOD.
Okay.
Apologies for Steve Williams. He was going to come in, of course, but he's been waylaid and letting out not to make it. But I've heard a bit of chat about some DOD projects. That's why we're getting started. I'm Mal Kadek, anyway. I'm I guess, founder and head of the Gap Geo group. It's a group of companies, 3 companies altogether, I suppose. But the main company is Gap Geophysics Australia. We specialise in mineral exploration work. We developed a lot of sort of technologies over the way. Developed the SAM technology, for example. We do a lot of deep penetration EM surveys. Some semi-airborne ones. You saw an example from Doug earlier. We have another company called Gap Geopack, which is the company that we use to actually build instrumentation. So we build very high power transmitters. We build our receivers, these SAM receivers, for example. I'm going to be talking a little bit about the UltraTem system, which is a very high resolution. Mark might be interested actually EM receiver for shallow detection work as well. We use it for unexploded bomb detection work. And the other company is GapEOD, which is what's up at the moment.
Which one would you like first?
Maybe GapEOD might be quicker. I won't spend too much time on it. But yeah, the third company is GapEOD, which again is a services company. It's a partnership with Steve Williams and Bridgewater Geophysics. So we specialise in unexploded bomb detection work, and we've built very specialised equipment for doing that. This is just a little bit of an overview of GapEOD, I suppose, because it sort of shows some of the developments that have happened along the way. I got involved in unexploded bomb detection work back in the early 80s, showing my age now, that we actually built magnetometer systems and delivered them to the Air Force back as early as about 1985. So we really pioneered digital geophysics for unexploded bomb detection back a long time ago. This GapEOD, we only formed, it must have been about 2013, I think. We got out of EOD for a while. We got a little bit bitten by the financial crisis back in the early 2000s. But anyway, we've since we formed GAP EOD, we've been doing EOD work again, explosive ordnance detection work again. A number of projects we've done there. That's been done with ultra mag. So this is one of our very high sampling mag systems, quad sensor array, cesium vapor magnetometers. So we've been working with those for 30 years now. Just another example of using the mag at Amoga, former army depots in Australia. So a lot of former military sites in Australia are contaminated with bombs, for example. So it's a real issue to actually clean those up. We've been using magnetometers historically. We didn't have access to good EM transmitters and receivers back in the early days. Another one, Majura, down in ACT, I think. So I won't spend too much time on this, but again, these are just mag responses that we're seeing from bomb detection work. You can see that they're quite clear. That one of the real issues with using magnetometers for UXO, of course, is where you've got lateritic soils which are very magnetic, sometimes quite hard to actually distinguish individual UXO type anomalies. So these are obviously very high resolution surveys. We've got sensors which might be of the order of 35 centimetres apart, where taking samples typically every sort of 5 centimetres or less along line, so very high resolution. More mag surveys, typically, this is actually up in Queensland on the Sunshine Coast. A lot of the Sunshine Coast was used as practice bombing ranges from ships out in the ocean, which they used to fire onto shore. This is still magnetics, quad sensor surveys down near Canberra. More mag surveys. So in 2014, we started building the UltraTemp system. So this is, instead of using magnetometers now, we're starting to use EM systems. So we've built our own 3-component cubes. So these cubes here are actual coils. They're 3-component coils. And we use those in an array, as you can see there, similar kind of line spacing and sampling, look what you'd be using for the magnetometers. You're looking for the same targets, very small targets, reasonably shallow depth. In this particular case, we're using a fixed loop. It's basically a fixed loop survey, a large loop. It's all a matter of scale, of course. A large loop in this case might be the order of 100 metres by 30 metres, so relatively small, but it's still a fixed loop. And basically, everything is GPS positioned and GPS synchronized and everything, as you can imagine. But getting very high resolution 3-component EM data from that. I've got a number of projects we've done with the UltraTemp. One of the first implementations, I would suppose, was with a little trolley like that, 2014. Just an example of some 3-component data there. I'm not sure what component data that is. Sorry, this is Steve's presentation, so I'm ad-libbing a bit. Another later version of it, so it's a towed array now, properly towed array now. We've rebuilt instrumentation, receiver systems are sitting on the back of the vehicle here. I guess not too dissimilar to what Dave does, really, just a different scale, of course. But yeah, towed array system, but you can see there would have been 8 3-component cubes on that. Another view of the same thing, I suppose. We've done one of the largest UXO EM surveys of Williamtown. So this is basically extending Williamtown Air Base for bringing in the new jet fighters, F-18s, were the new ones anyway. But yeah, so very contaminated, and all these are items of UXO and clutter and everything. Steve himself is a specialist in discrimination. He actually worked with Doug, his postdoc with you, didn't he, Doug, I think, and worked very much on discrimination of ordnance from clutter. So the whole reason for that is to get very high quality 3-component EM data to be able to determine what's scrap, what's actually really at UXO. And so it makes a huge difference to the digging costs and digging process if they can actually reduce the amount of digging by discriminating between what's real UXO and what's not. Who's that bloke?
I don't know, pretty handsome.
Yeah, another survey being done on the Sunshine Coast, Australia. Dan was there. More examples of the sorts of surveys we get. You see the number of anomalies sort of showing up in that particular case. This is that you as well? No. This is actually using the ultra-temp system for the detection of GETs. You may not have heard of that terminology before. GET stands for ground engaging tools. So this is a real problem in some of the mines where the large excavators, large ripper teeth might fall off a machine, if you like, and get lost in the stockpiles. And the big issue with that is if they go through to the crusher, they can actually cause a lot of damage to the crusher. But secondly, cause significant downtime. So you might have a week of a crusher not working, which could cost millions of dollars, to these mines once they're in full production. So basically, this is an amazing survey, really, because it's actually finding items of steel items in the magnetite stockpile. So it actually worked extremely well. Some of the items that were detected there on the right-hand side, and just kind of what the maps look like.
You find that hard hat?
Sorry?
You find that hard hat?
Not the hard hat. I think that was the scale. Just another example of using the ultra-temp system for GET detection as well. I didn't mention, by the way, we use in Australia operates at 25 hertz. So this is a true time domain system operating at 25 hertz for the sake of our power frequencies here. So relatively low frequency. Yeah, just more examples of things that were found in the stockpiles. We've had a system working in the and Ho Chi Minh Trail basically for a few years now. This is for the LXL mine. That's the pond. But we've actually leased systems to them. So they've had it now, I think, for 2 or 3 years. Do you remember, Crystal? I can't remember. But it's been working very successfully. Prior to going over there, everything was just done with analog systems. So there was no record of what was found. People could have been sleeping under a tree as far as anybody knew, because there was no actual documentation to show what had been done. There's no GPS positioning or anything. So you can imagine with items this small, we need to have very high precision real-time kinematic differential positioning. GPS. For very 2 centimetre accurate positioning, if you like, for bomb detection work. It's a system working in Laos. That's a Rio Tinto company, you probably know. So that's actually working quite well. So in Laos at the moment, we're using one of our high current transmitters. Geopack actually builds the transmitters for these things as well. So we have a very small transmitter, which I can show you a photograph of later, which generates up to about 200 amps in relatively small loops. So we use them for moving loop EM surveys, for example, as well. That's what they're originally designed for. But you can see the sort of results that we're getting with that. Different implementations along the way. It was 2015, so that's a quad sensor hand carried array over mine. Again, difficulty doing EM, and not in magnetite soils in this case, but very conductive soils. This is copper. So not easy for doing EM techniques in short term usually. Just more examples. Sorry. We've got Fluxgate systems doing downhole EM in Germany as well. So we've been working with a company there called Heinrich Herdes, and they're responsible for actually finding large bombs which are leftovers from the Second World War, which are still within villages, for example. So it's quite common to be doing surveys between houses, in places like that. Yeah, just another example of them digging one up. It's amazing the inversions the guys are achieving, though, on some of these sorts of items. But in this particular case, they actually model it as being 2 items, similar in size, I think, to a Mark 84, but it actually broke it in half. They were actually able to detect the two parts to the bomb. This is black dust, by the way. Of course, you know. Yeah, so borehole stuff, you know, using say 3-component flux gates in this case, and also being used in Laos. Because we're working at the moment still actually in PNG, and so this is clearing sites for putting pipeline in actually in PNG. I just recently done a job for Rio Tinto again. Their caustic bladder actually up in, I won't talk about that, I got into trouble as well. So we've just done some more work down at Williamtown as well with the ultra-temp system. And just the other thing to mention is that over the last 12 months, I suppose, we've deployed a marine system, a marine sub-temp system, which has been operating in Portsmouth Harbour. So it's actually a number of different transmit loops, several loops which are firing independently with a whole array of 3-component flux gate sensors, coils and sensors on them. But that's being towed behind a tug, if you like, along the bottom of the ocean. It's actually mounted on a sledge, weighs about 13 tonne. It's got to be towed along the bottom of the river for clearing it prior to bringing these new $1 trillion aircraft carriers into Portsmouth Harbour, actually. So it's really quite interesting projects going on with GAFIOD at the moment. You want to find me up on the next one?
So like a
So
summary page of all the different mag instrument names, like a ultimate mag and another than and as a start on what would all these acronyms mean? Well, how are they?
We've got Ultra Mag, we've got Ultra Sam actually. Same thing. So this is, I'm going to talk a little bit about SAM at the moment. Doug talked about a HeliSAM survey before, and I'd like to talk a little bit about the reasons for developing that technique. Chris actually talked about SAM and its application for very high resolution, shallower measurement. And in fact, it was the original reason I developed SAM. It was actually the subject of my PhD work back in the early 90s. But well, going back even before that, I did my master's degree on IP back in the early 80s. And one thing I was looking at with IP was just how undersampled the electrical fields were with, with these fairly sparse arrays, if you like. Prior to that, I've been working with the high resolution magnetics, and I kind of put 2 and 2 together and thought, well, if I can actually use something like a magnetometer to measure electrical responses as well, and get the spatial definition with the electrical fields that we can achieve with magnetics, that would be quite a valuable technique. Hence the concept of SAM was born. But so what I want to talk about here is not the high resolution applications for SAM, but in fact its application for deep penetration surveys, as per law, which Doug mentioned. So basically, I tend to think that in mineral exploration, we sort of believe that we've picked the low-hanging fruit. We found the easy stuff, the mineralisation, which is basically quite easy to find near surface, has probably already been found. So really, the future of exploration is going to be focusing on more subtle or deeper or more difficult targets. If you start looking deeper, drilling becomes more expensive. So I think we're going to become more dependent on geophysics to actually minimise our drilling costs, if you like, have more focused drilling campaigns. And the other point I suppose I'll make there is that, normally mining companies have got pretty tight budgets these days, so you really want to get the maximum for your exploration dollar. I talk about viable exploration depths here. I think in terms of viable exploration depths, I'm thinking about what's actually mineable. Typically the top kilometre, I suppose, is what you'd call mineable. If you're finding a new ore body at a depth below that, chances are it's going to require too much cost to actually get down there to mine it. The engineering becomes far more expensive. So probably not really all that useful. And really, if they're a small deposit at that kind of depth, they're not so much use to us either. I mean, if they're going to be deep, they've got to be large. Shallow exploration, I call 0 to 300 metres, and they tend to benefit more from high spatial resolution. That's where things like our standard SAM high resolution conductivity map comes in, and other techniques, of course. Deep exploration, between 300 metres and 1,000 metres, I'd say you get much less guidance from surface exploration, from geology. You get further away from the surface, you know less about what's going on at depth. So, and the other thing I'll point out is that the deeper the ore body, if you're looking at EM responses, the longer the wavelength. So this has implications in terms of your survey design. If you're going to be looking at EM responses from somewhere pretty deep down, you've got to have lines which are long enough to be able to recognise a response. So that's kind of key to what I'm talking about here, the need for larger scale if you're going to be looking deeper. As I said before, if we're looking for deeper ore bodies, they've either got to be very high grade or they've got to be large to be viable. I also think that statistically, if you can cover more ground, you've more chance of finding something. So for a given exploration budget, the more ground you can cover, the more chance you've actually got of actually getting a response that's valuable. So for doing deep penetration, we need to have larger scale surveys. We need to have greater sensitivity because the signals are so much weaker. You need to have a lot more transmitter power if you're talking about EM, of course. We also need, because of the scale of the surveys being so much larger, you've got to have much more efficient acquisition. Otherwise, it just becomes cost prohibitive. So really, deep penetration surveys are very challenging. They've got to be bigger, they've got to be better, deeper, faster, and cheaper if they're going to work. We talked about SAM a little bit before. We're using a transmitter. It can be either a dipole, as you saw with Chris's presentation, or we can actually use a fixed loop, as you saw with Doug's presentation. What we do is actually, we're kind of using the Earth's magnetic field, if you like, as a carrier signal, and we're using a total field magnetometer to actually acquire data about the Earth's total magnetic field. But the Earth's magnetic field's got a modulation sitting on top of it due to the transmitted signal and the response of the Earth. So what we do is basically acquire the whole of that data, and then we digitally separate it. We filter it off, separate the high frequencies from the Earth's magnetic field variations. We do conventional sort of processing on the square waves to get your EM responses. There are a number of parameters that we can extract from it. We get magnetics, of course. We're using a total field center. We're getting total field magnetometric conductivity if it's an NMR type survey, EM or potentially IP as well. Types of survey configurations we have. This is kind of key to why SAM works. There are a number of different EM sensors that people use typically for doing EM surveys. Coils pretty common, flux gates we've talked about as well. Squids are an excellent sensor. They're very, very expensive, I suppose, but they're very sensitive sensors to use. And of course, the cesium vapor is the one that we use. They have different performance characteristics depending upon the frequencies that you're looking at. Coils are better at high frequencies. Cesium vapor and squid probably better at very low frequencies, at true B field sensors. So in terms of deciding what sensors you're using for a particular survey, you need to sort of know what kind of conductances, what kind of time constants you're looking for. But high conductance ore bodies, which is what I'm talking about today, will benefit from having B field sensors as opposed to the BDG, just because of their very slow decays. The key difference between all of those sensors and the cesium vapor is that the coil, the flux gate, and the squid are all vector sensors. They measure changes in the magnetic field in that specific direction, specific vector. The difference with the cesium vapor is that it measures variations in the direction of the Earth's magnetic field, so it's a total field sensor. From an application point of view, the real difference there is that there's no orientation or leveling required. So if you're using a coil or a flux gate or a squid, you've got to level it, you've got to orient it. and you've got to make it very stable while you're taking a measurement. It's not the case with a cesium vapor sensor because it's a scalar sensor, it's not directionally dependent. So it means that we can acquire data while we're continuously moving without any rotational noise due to the movement of the actual sensor itself. SAM waveforms is pretty typical, sort of a time domain waveform. We measure MMR during the on time. We measure EM during early off time typically, and there's potential for measuring IP at late off time for low transmit frequencies. Sorry, I won't go through all that stuff. Just a picture of the mag itself. It's pretty ugly, but it's a pretty high precision instrument which is capable of measuring the Earth's magnetic field at rates of up to nearly 10 kilohertz. So for a total field magnetometer, it's a very, very fast and quite sophisticated system. We can use it in walking mode like these guys here. We can be towing it when we're doing salt-like work, like Chris mentioned earlier. We tow it on a sled, so we can do 10 kilometres per hour on a salt lake, for example. We also use a helicopter-borne system, as we did at Low. We have developed a UAV system, as you can see in that photo there. It works fine. We're still having logistical issues with that, with navigation software mainly, and so yeah, a few things to sort out before it becomes commercialised. If we're doing extremely sensitive measurements, very deep search, normally we'll use Samson mode, which is the stationary measurements, or acronyms. So in this particular case, we might be using transmit frequency of 0.125 hertz to be typical. The big 5 minute readings is what we're commonly doing. We've got Samson surveys happening at the moment. Photographs there is a Samson system working in Atacama Desert and in Finland. So I mean, we've worked a fair bit around the world with them. The other thing I just wanted to point out here is that data quality depends upon a number of factors. So we talked about cultural noise and tour noise and operator skill. If you've got an active source like you do for an EM survey or an IP survey, it's not just the sensitivity of the receiver that matters, it's actually the strength of the signal you're transmitting as well. So one thing that we have put a lot of effort into over the last decade, if you like, is building very high power transmitters for deep penetration or high quality surveys. My point here is that if the transmitter system isn't powerful enough to induce a response from the conductor, it doesn't matter how sensitive your receiver is, you're not going to see it. So it really is a combination of transmitter and receiver which make these surveys possible. At Geopack is the company that we use to build our transmitters. So you see we have a range of different options that we build. There's no one transmitter that suits all applications. One thing we learned fairly early is that large fixed loop type arrays will benefit from high power. You don't have to move them around very much, but chances are they're not very portable. If you're using very resistive galvanic dipoles, you want high voltage. If you want EM, you want high current. It's very difficult to build all these things into one transmitter. If you're working in inaccessible areas, you want portability. So, depending upon where you're working, you've got quite different requirements. So we've built a range of transmitters to actually suit the requirements that we have. This is the latest of our high power transmitters. It's called the HPTX80. And if any of you are familiar with doing EM 10 years ago, typically the maximum current you might use for a survey might be of the order of 15 or 20 amps is what you might put into a loop. So this transmitter is capable of up to 360 amps. Typically, if we're doing downhole, deep penetration downhole surveys, for example, we might be operating in the 150 to 200 amp range. So the signal to noise ratios that we're achieving with these systems are kind of unprecedented. It really has revolutionised the quality of surveys that we're seeing in the industry at the moment. If you want high voltage surveys, we do have a high voltage transmitter. It's a portable system designed to be slung into places if need be for poorer access. We've limited our voltages to 2500 volts. There are practical constraints and safety constraints into what you can actually use in the field as well. So that's something that we're very aware of as to what the limitations might be from a safety perspective. Our Moving loop EM transmitters are, very designed to be portable because they're moving all the time. So in this case, we've got very high current, they're capable of up to 200 amps, but you can see they can fit on the back of a little ATV or UTV, so quite easy to move around, really. We talked about MMR surveys before. If you're talking about deep penetration EM, we talked all about the theory behind EM. I just wanted to show you a little bit about, comparison of airborne versus ground EM surveys. Airborne EM is obviously a great tool. It's an amazing tool, and it gives us the ability to do rapid survey coverage over large areas. It's relatively cheap to actually deploy for the area that's covered, so a great tool. But you're going to always be limited in terms of the depth of penetration with an airborne system. You have to be. There's a reason for that. Firstly, typically, if you've got fairly high transmit frequencies, I'm talking about time domain at the moment, by the way, much higher with frequency domain. So typically you're operating at 25 or 30 hertz, so your decays are normally limited to roughly 10 milliseconds or thereabouts. You've got very short stacking periods because you're moving so quickly, 80 knots typically. You've got quite low transmitter power compared to ground EM surveys as well. And all those things basically limit your depth of penetration. Ground level EM is great. We can have much lower transmit frequencies to get better depth penetration. We've got the ability to have longer station occupation time, so better quality data because we can stack longer. And you get higher transmitter power than possible with an airborne system because we have the ability to have a much larger generator and a much larger loop than you can actually deploy from a helicopter. But there's drawbacks. Stationary readings are needed, so it's slow and it's expensive. And of course, say budget constraints always seem to dictate quite wide line spacing and station intervals. So what I commonly see is that EM profiles are pretty generally undersampled. Typically 400 metre type line spacing is not uncommon, 200 metres at least anyway. So again, from a development perspective, to have a system which could actually acquire data quickly and still have deep penetration would be a good way to go. We talked about transmitters again. Doug talked a fair bit about that, and just a comparison of different transmitter configurations. We've talked about helicopter-borne systems. Typically, they might have a loop of 20 to 35 metres in diameter, like the SkyTem or VTEM systems. Moving loops at ground level might be usually 200 metres by 200 metres is quite common for our surveys. Fixed loops can be much larger. They can be kilometre by kilometre or even more. If you're dealing with airborne systems, the currents they're generating might be hundreds of amps, but they're actually into a fairly small loop. Ground surveys typically has always been sort of 10 to 40 amps would be quite common. But the power of the transmitter system is called the dipole moment, and it's the dipole moment which really gives us the ability to get depth penetration. Just as a comparison, I know Doug talked about SkyTem systems. I think your figures might have been from 2006 or 7 or something, and the moments at which they were quoting were of the order of about 0.2 million. The latest SkyTem system that I've seen has got the 512 system has got a moment of about 3/4 million meters square. The highest powered one that I'm aware of has got a moment of about 2 million. So remember, the dipole moment is a function of the loop size as well as the current number of turns. So just a quick comparison of dipole moments and magnetic flux from an airborne system versus ground system. Just for comparison, I'll just put a model to play to you, just 250 metres by 300 metre plate. It's at a depth of 500 metres. Just put a little bit of a dip on it at 30 degrees. So they've got a plan view on the left-hand side, and a view from the south in this particular case. If you put the highest powered helicopter-borne system, like a HeliTem system, over the top of that, as I say, it's got a moment of 2 million. And the helicopter loop is actually an elevation of around about 40 metres. Then the flux, which Doug was talking about, we're getting through that particular plate at that depth, is about 145,000 Weber. So if you compare that to a ground system, a moving loop EM system on the ground, with exactly the same moment, 2 million, and you could achieve that with a 200 metre loop with a Song ZG30, for example, 2 turns, you might get 50 amps out of it if you're lucky. And the flux goes up to about 168,000. And the reason for that is that the loop's now on the ground, it's not in the air. So this is just purely comparing your flux. You go to a larger loop, so we've got a 400 metre loop now with exactly the same transmitter, limited power, so current goes down. So we're 25 amps instead of 50, but the loop size is twice in both directions, 4 times the area. So the moment's gone up to 4 million. The flux is now 278,000. So the flux has gone up a fair bit with exactly the same transmitter, same power in the transmitter, but with a larger loop. So depth penetration is very dependent upon loop size. It's obviously not going to have a 400 metre loop under a helicopter, you know, so that's one of the real constraints with an airborne EM system. So if we go to a 400 metre loop now, but now we've got one of the HPTX70s on it, the high power transmitters that we build. So instead of having a flux of 270,000, we've now got a flux of 2.5 million, and we've got a moment of 35 million. So as I say, it's chalk and cheese, you know, you've got a huge dipole moment now compared to what you can possibly achieve with any high power airborne EM systems. Go even further with an 800 metre loop with a conventional transmitter, you can generate a moment of 1 million. That's with a conventional transmitter with 40 amps. A high power transmitter can probably put 4 times that. So the flux has now gone up to 4 million. So obviously, the larger the loop, the more power you've got, the greater your dipole moment, the more chance you've actually got of getting a response, inducing a response from the conductor at depth. And just finally, a fixed loop EM system, 1,000 by 1,000 metres with a conventional transmitter versus the HPTX with, again, with a moment of about 4 million. I think it's just important for a lot of our clients, my clients at least, to sort of understand what the limitations are with airborne EM, because there's a lot of dependence upon them as being the be all and end all, but they're not. It's just a dipole moment comparison. So this is the highest powered helicopter-borne EM system compared to the moments we're able to generate with the ground loop. So anyway, as I say, Airborne's got some limitations in terms of depth penetration, although it's a great sort of reconnaissance tool, mapping tool. I don't need to go to too much more detail here, I suppose, because Doug's already shown you the Layla example. But we have a couple of case studies. One was from the Forestania EM test range in Western Australia, where we actually compared SAM in a moving acquisition mode, dynamic acquisition, non-stop recording over a couple of known conductors, and compared that with stationary readings with Samson. Let's say there's 2 conductors there. They're called IR2 and IR4. IR2 is quite small, 75 by 75 metres. It's less than 100 metres deep, and it has been seen with airborne EM. It's detectable with airborne EM. IR4 is not detectable with airborne EM. It's closer to 400 metres, 350 to 400 metres down, but it's actually much bigger. But we put a couple of loops around each one of these. L1 loop is around IR2, the small one. L2 is around IR4. And we surveyed it with SAM in both dynamic acquisition mode and in Samson stationary mode at quite different frequencies. This is Samson mode, and I'll just point out that we're using HPTX70s, kilometre by kilometre loop, 150 amps, so I mean a lot of power. But the noise levels, you can see that we're able to achieve with a ground servo like that of the order of 0.005 picotesla per amp, like incredibly small noise. This is actually the profiles acquired dynamically with sound. This is without even stopping to take a measurement. So, look, just to run forward a little bit, this is a response from Samson, which at 0.125 hertz. This is a response from SAM. We can cover a lot more ground because we're not stopping to take any measurements, so it's very, very quick. But still very definitive of the fact that of IR2. This was the shallow conductor. But, same thing with, we go to IR4 as well. So this is Samson mode. It would taken a couple of days to do that work. This was done in one day, 25 kilometres of surveying in one day in SAM mode, EM mode. But you know, obviously not going to miss that response either. And that's from a conductor which is nearly 400 metres down. So comparison cost-wise, of course, is quite significant as well. You know, a couple of days of surveying compared to a week if you're doing stationary measurements, typically something like that. But anyway, as I say, we did that trial to basically, first of all, determine ourselves whether dynamic acquisition of a total field sensor was able to get good quality EM from a very deep conductor. And on the basis of that knowledge, we took on the LALOR project with the LESAM system. So this is kind of what led up to it. And this is the LALOR case study, which Doug's already talked about. It was done in 2014. Chris actually was there. But just in terms of some of the logistics of it, we've seen those images before as well. Remember, it starts very deep, nearly 600 metres, goes down to well over 1 kilometre. So very deep. We flew 93 kilometres of surveying in 2 hours. To do that at ground level in a place like Canada, first of all, they'd have to do it in winter when everything's frozen, because part of it was under lake, I think. They had to clear all the lines to actually get their instruments in there to actually do the acquisition in the first place. So it would have been weeks of work to do a couple of lines at ground level, for example. But admittedly, the loop was already out. It had been used as a test loop for a while, but the acquisition time was sort of very minimal. The other interesting thing about this, and it comes back to what also Doug was talking about, is that we didn't have one of our high-power transmitters there. We just used a local Phoenix transmitter. So the loop was about 1.7 by 1.7 Ks, but only able to get about 20 amps into it. So this response was generated from only 20 amps using a conventional transmitter with a conventional loop. But again, the loop size meant that we've got a moment of 57 million compared to an airborne system. So this was not detected by airborne EM systems. And you saw the response. This is the magnetics. You can see the outline of the ore body in there at the moment, and the loop. As we pointed out the other day, this is actually a power line which runs adjacent to the loop. So the power line was earthed. Basically got all these circuits set up with the steel poles and lightning circuits and things in it. But so acted like a really nice conductor in early time. Obviously, as you step through time, the response from the power line dissipates, and the response from LALOR shows up. And again, this is 7.5 hertz as opposed to 25 hertz, so we've got much longer decay times to look at compared to conventional airborne EM system as well. There's the last window there. Yeah, so it basically has been a Peter Fullock has also done 3D inversion of that data as well. But I think what I was getting at in Australia is that we've got quite a lot of conductive overburden here, and it's not so easy to get that kind of response from something at depth in our situation. It's a pretty resistive area there, which is why we're able to actually see that response at that depth. But it's going to be important in Australia for us to be able to use very low transmit frequencies, to use high power to actually get through this conductive cover to see things at depth. We're able to locate to see Nova Bollinger, for example, if anybody's familiar with that. It's at a depth of roughly 500 metres in the Fraser Range in both Samson mode and SAM-EM mode, dynamic acquisition mode at 3.125 hertz. So I think that the helicopter-borne system, LESAM system, is actually going to be a great way to be doing systematic acquisition, big penetration surveys. Sorry it took so long. Any questions?
So should we can do a quick coffee break
Yeah.
and then regroup?
Yeah.
And so
Is coffee up?
if not, I'm sure she can bring it up.
Let's stretch your legs and do a quick coffee break, and then come back and do a bit of simpeg and a bit of tutorial on MT.
Hey Todd, I have a question. Is anisotropy make sense for chargeability at all?
I don't
You don't know?
know. There might be some effect because the chargeability builds up depending upon the currents.
Yeah.
So if you've got something that's anisotropic, then you get more current flowing this way than that way.
Yeah, just
So
it was a question when I was working in this last project and the massive sulfide lens that I was looking at. It's this thin lens. I was like, I don't know how big it is. I mean, the thickness like this way is nothing, and
Right.
it's
Yeah.
the other way around.
Couple meters.
Yeah.
Right.
Yeah, not more than that, and then extend sidewise. And if, with resistivity, if you could have such a small wavelength that would pick up just that little target, with inductive sources, because you just at the end as you average, if you look at such a large area and you pass that, we have sediment on top, and you pass that and you see the large area, you don't see really that little change. You know what I mean?
But even if you have a plate, and that's what you have, right? You basically have a conductive plate there, right?
Yeah, but you just see the country rock that is resistive. You don't see that. As soon as you hit, there is a conductive layer, then you have the country rock that is resistive, and then you have the sulfide lens. So
Right, okay, so that's fine.
Yeah.
So where does anisotropy fit in?
But I just thought if it was based on resistivity, if you can measure this way and perpendicular along the.
Oh, I see.
But does it make sense for chargeability? Because one way rather than the other way around, I don't know. I just was a question.
Well, okay, but the chargeability doesn't necessarily have to be anisotropic, but your chargeability response will depend on both of these, right? Because if you're really nicely coupled this way, okay, for the DC resistivity, then you're going to get currents that are going in through there. They're going to build up charges, and you're going to recognize that, okay?
And the other way around.
If you go this way, you're going to get different currents, right? So you're going to get, your chargeability will also be different. So the response will be different. So at a microscopic level, there's no necessarily anisotropy, but depending upon which way you're actually illuminating things, you will get different responses.
It's not like,
So that's more of a coupling issue as opposed to being intrinsically interesting.
and you think you can see that with resistivity? Why don't I see any? Why I don't see anything in my models? I just see this country rock that is resistive. The chargeable source for the resistive country rock. I don't pick up it as a conductive lens.
So how conductive is the top region?
It varies. It goes up to 50 meter, and the resistivity is like 10 meter.
So you're actually getting much current that's going into that lens?
How do I know that one? What do you think?
Well, I don't know. You'd have to
I don't know. I don't know because how would I? I mean, it's one of my questions. When we talk about the bottom of the conductive layer, do we really see the bottom when we talk about inductive sources?
Yeah.
What do you think about the bottom?
Yeah.
You hit the inductive source, and we talk about how the energy disappears because of the conductivity. But how far it goes? when I did MT, I would put, you would make changes at the bottom of that thing you were looking, and if you inversion to pick it up, you would say, this is how I did it. Okay, this is penetrating. Fair enough.
Fair enough.
Really, it would show, I'm not picking, and when I say to people, there was partial match from 30K to 90K. It wasn't going to 90K. It was just not going more than 65 or 70K or something like this, because it wouldn't go with that.
Just based on skin depth.
Yeah. And yeah.
But if you've got sufficient depth of penetration, there's no reason that you can't pick up the bottom of that conductor as well as the top.
So that's the problem. You're right. I mean, that's it, right?
It might be.
What else?
There's something that you say that's kind of interesting. There's a deposit in Canada. It's a porphyry deposit. It's Mount Milligan.
Okay.
And there was really not much of an IP or a DC response to it.
Yeah.
It almost looked like we weren't seeing deep enough. And yet, if there was an IP signature that was being picked up, so it doesn't sound too dissimilar. There's some current that's going in and enough to maybe charge things up. And then you see it because you're just looking at the secondary field. There's nothing else that's around. There's.
What's that deposit's name?
Oh, Mount Milligan.
How do you spell it?
M-I-L-L-I.
You know, there's a website called Hacker Text.
That's
We did. I'm not sure. Well, that is kind of published. Yeah, we actually wrote a small paper. I think we captured the DC, the results for the DC resistivity inversion, which didn't really show anything. But the IP was a real signature. So, yeah, these can happen. And what about the? Do you think that lens sulfide actually is really conductive? I mean, maybe it's just not conductive. Maybe it's just charged. So you're just not seeing it.
I feel I'm upset.
I haven't thought about it. I don't know why I assume it should be conductive.
Because I mean, not all chargeable bodies need to be conductive, right?
Yeah, I know that one. But I don't know what it's like. Maybe it's not.
Essentially, companies.
Yeah, that's good.
That's
He knows all that.
There we go.
our first bloody
So that's big extent. So same deal. We look at the project.
It'll go to the next one. Your voice decline like
yeah, well, this is the other thing.
Sounds interesting. So it's not.
The other thing I was trying to look at some of the stuff and just right.
That's really.
This one.
I'll have a dig around but essentially, yeah, so the most recent rounds,
you got
wow, it has to.
And we'll get involved in so it's really amazing.
Just another line.
That's exploration technology trial.
Yeah, it is. It is.
Do you only do 10 years as well?
I'll find out. Submitted the folder assessment criteria.
Yeah.
You can see how it's going to be measured up down the tunnel.
Yeah.
Well, it doesn't have to be 5 drill holes for this.
We're going to talk a little bit about Simpeg. So Lindsay's going to take you through a quick overview of Simpeg, and we'll probably go on to looking at tutorials and maybe the apps. Yeah.
Did you do that immersion again?
And she's heard setting some things up, but I think the main thing will just be to go through the tutorial that talks about some of the issues that are associated with the inversion, and then you kind of, yeah, you kind of get what things are done.
Expand like let's read one that is looking at like Nostradamus. No, it's still still, mine's busy. She's a little man. And you have to put it behind the screen or something. I know that. Maybe that's some process.
That's only 15 else has one. Yesterday, I didn't see you here, I just went through
Yeah, no, it's pretty. Should have seen him walking out of there. Like literally, he's behind stuff.
Does that help a little bit?
Yeah.
Okay, perfect. I think most people are back from the coffee break.
So what I would like to show now is SimPeg and some of the open source resources that we have. I'll show you how to use them and also where you can jump in and get involved if you're interested in contributing content or contributing code or using code, anything like that. There's room for all of those sorts of things. So I'll start from GeoSci.xyz. So I introduced this briefly yesterday. I went through, EM is the main resource that we've been using in terms of a textbook for this course. That's where all the case histories are. That's also where we've got background on all the geophysical surveys and methods. And so if there are things that you're interested in adding to that, one of the things that we've been hoping to start building up there is actually more information about systems that are out there. So that's a great place to jump in, is if you're familiar with different EM systems and you would like to actually write out some of the specs and give a few examples. That's certainly a place that you can jump into. SimPeg we briefly introduced yesterday, and I'm going to spend a little more time on it right now. So this is the software for simulation and inversion in geophysics. This has been a big group effort at UBC primarily. There's also students who've been involved from Colorado School of Mines, a few people at Calgary. So we're trying to branch out and have this be contributed to and used by a broad audience. The code is stronger when there are more eyes on it, and so that's part of what we're trying to accomplish here. So this is the main website you'll see with SimPeg. So there's a few resources here. There's the paper that's been written and submitted to Computers and Geosciences. Recently there was one that we just submitted on EM, so we'll add a link at some point here as well. Please do feel free to stop me if I start rambling on that, or if you've got questions and things like that. So one of the important things off of here is the documentation. So this is a great place to jump in if you want to sort of see some examples of using SimPeg. So here we've got an examples page. And so there's a number of examples. We've got the Buchronon, we've got an inversion from there. So we do a 1D stitched inversion, and we also have one where we'll do a 1D inversion of both the SkyCam and the resolve data. So you can see the frequency versus time domain inversions, how the setup works in SimPeg and all of that. And so those are free to download and use if you'd like. Another thing to highlight here is it's not actually just specific to electromagnetics. We've got other methods in here as well. I mean, the goal is that SimPeg becomes a place where we can simulate and invert any type of geophysical data. So we've got potential fields, we've got gravity and magnetics, DC resistivity, there's some IP in there. Then we've got frequency domain and time domain, as I've mentioned, and then there's also natural source. So magnetotellurics, or if you're looking at Tipper data. There's also, for people interested in fluid flow, there's Beto zone flow as well that's linked in that. And so here, this is a good place to start. There are a whole bunch of examples. Plot it, produce a picture, all of that. One other thing to point out is we've got, so if you look for, there's a Google forum on SimPeg, and this is a place that we're using to ask questions, ask and answer questions. So if you are getting up and running, and examples in the documentation are a good place to start, but basically, if you want to extend it or do something new, you want to talk to somebody. And so this is a good way to get in touch. Perfect. So now, if we go back to EM GeoSci, as we mentioned before, there are the ways you can sort of jump in and contribute. If there are things that you want to edit, you're welcome to do that. I'll show you just kind of what that looks like briefly. So it brings you to a GitHub page. You can go in and change the text, anything like that. If you were interested in, in adding something new and weren't too sure how to do that, you can send us an email, or you can create an issue, and that's just like a notification that says, I'd like to help set this up. and then we'll be in touch and help make that happen. Okay. So what I'd like to do with the rest of our time this afternoon is we looked through some of the EM apps yesterday. These are the ones where we've got the slide bars set up, so you can just go ahead and be running SimPay code and driving it from a GUI. But the other set of notebooks that we have actually expose all the code. And so that's what I'd like to go into today. And so really what we're trying to accomplish here is, to give you enough of the tools and enough of the context to figure out how to set up and run your own simulations and versions. And so what we're going to start with here is an MT tutorial. So this was recently published as a part of the Leading Edge tutorial series. I don't know if you've seen that before or not. Has anybody seen the Leading Edge tutorials? A few heads nodding. So it's the only open access publication that the SEG does. And it's organized by Matt Hall. And so it's, you've got short articles, and then it's also a set of Jupyter notebooks that go along with it. And so the goal is to be able to actually get up and running with whatever tutorial content you have there. And so that's what this is. So we've got a suite of notebooks here. So there's five of these notebooks. So I'm just going to quickly go through the first one. We're not going to really walk through it in detail, but you can find all of these, as I mentioned before, from the EM GeoSci apps page. So the first one that we've got here, we're going to go ahead and clone this. And so what we're going to do in this set of tutorials is actually set up a finite difference approach for modeling MT data, just in 1D. And we use some of the SimPay framework in order to do that. And then we're going to explore one example of non-uniqueness in MT data. And then we'll go ahead and run an inversion. And then we'll see how much time we have, but I did try and set up your example from this morning with the layered model. So we've got the forward model and a quick inversion running. So we'll see how that goes. Is everybody who is interested in following along able to find these notebooks? Okay. Can you see the screen from the back, or is it too small? A little small. Okay. So here all I'm doing is just installing SimPay. If you set this up and download it on your own machine, you won't need to do that step every time. But because we're getting sort of a clean install from Microsoft, we do need to do that install step.
Sorry, and this is going to work on Windows, this part of it, with the SimPay.
It'll work on some Windows machines. It depends on which version of Visual C Studio you've got.
Yeah, so that
yeah.
Download C++, Visual C++.
Yeah.
I think that didn't work.
So we're working on getting that fixed.
Okay.
But yeah, right now, if you want
So this part, even if I go to a notebook, it's gonna go back to SimPay, and if it doesn't work on my machine, it's not gonna work here, right? That's my question.
If it doesn't work on your machine, it'll work on Azure notebooks still.
Oh, okay.
So you can still run this because this is a server somewhere that Microsoft is giving us that runs Unix. Yeah. Most Windows machines have been fine, but we've run into a few that are campy. So all I'm going to do here is import some of these are standard Python packages. So NumPy does matrix linear algebra, SciPy Sparse just does sparse linear algebra. And then SimPay, what we're bringing in the mesh class. So if you have a look more at the website, things like that, we've got pictures of the SimPay framework and how we've organized things. And I might flip back to that as we go along. But what the mesh class has, that's got all of a bunch of different mesh geometries. So you can start with sort of the simplest tensor mesh, but we also have octree meshes and curvilinear meshes, those sort of things in there. And so once you actually build up a mesh, then we have all of the finite volume operators that come along with that. So you can actually construct your mesh and then have all the mathematical tools that come with that. Utils is just some handy utilities. And then solver, we plugged in some decent solvers, because there's some good ones in Python, and then we've also helped just interface to some others like Pretty. And then matplotlib just to apply. So we'll bring all those in. Here, I'm just going to blow through this pretty quickly. We won't go through it in detail. What's going on in this example is we're actually explaining how we set up and discretize the 1D MT problem. So where we're putting things in terms of cell centers, faces, edges, and all of that. What our matrix system looks like, what our right-hand side is, how we're incorporating boundary conditions. All of those details are here. So, but I won't go through it in detail because I think 315 on day 2 is a bit much. So once we actually have the system, we set up a mesh, make sure it goes far enough so that we satisfy our skin depth, and also that we have fine enough cells that we're really capturing those high frequencies. And then from there, what we do is go ahead and once we've got the mesh, we can set up our system. So here you see that we've got a grad, we have our match matrices in a div. And then when we set up the A matrix, it just mathematically can look like that. And then we can go ahead and compute data from there. So that's all that notebook actually walks through. What we're actually going to do now is just use it. So if you would like to go in and see the details of how that was set up and solved, you're welcome to walk through that notebook and then get in touch with any questions. So we're going to jump over now to this notebook. So this is the second notebook. So we're going to actually have a look at an example of non-uniqueness and play around with a few things like mesh setup. This is the MT tutorial 2. So again, just doing imports.
It's doing that automatically, isn't it? Just doing the imports. It's happening automatically, isn't it?
No, sorry. What I'm doing here is doing Shift-Enter to run.
To do that?
Yeah, to run each of the cells. So you can either do run cells, or Shift-Enter is the.
We have a run that's grayed out.
Okay, so in that case, what you need to do. Because you're seeing something like this that's grayed out, right?
Yep.
So you just need to click on this guy here, this clone library button.
Yep.
And that will then give you your own copy. So that should take a second. And now are you able to see something that lets you run it? Okay.
It's cloning. All right, here we go. Non-uniqueness.
Were you able to get it going?
Yep. It's coming up. Yep. So in each one of those windows, we do control what you said.
Shift-Enter. All of the shortcuts are available here. So you see the help keyboard shortcuts.
What happens if it says dead kernel?
Okay, so sometimes what happens is you get a bad machine. It should restart the kernel. So you can do kernel restart, and then that should get you going again.
Yep, okay.
Okay, so now we've brought in the packages that we want to work with, and we're going to set up a model. So in this case, we're just going to do, let's start with the half space. And we're going to explore setting up a mesh, what you need in order to do that, and we'll compare it with an analytic. So here we've got a 100 ohm half space, and then the sigma, or the conductivity is often what we want to work with, so we just take the reciprocal. And then here we set up which frequencies we're going to look at. So we're going to look at 25 frequencies between 10 to the -3 and 100 hertz. And then one of the most important things to look at when you're designing a mesh is the skin depth. And so here we just have a little function because we're going to want to be using this a few times, which will compute the skin depth based on the conductivity and the frequency that you give it. So when you want to determine how small your smallest cells need to be, in that case, what you want to look at is basically how quickly are the fields changing in my most conductive unit. So in that case, you need to consider your most conductive unit and the highest frequency. And so here, when we do that, we look at our half space, because it's just one conductivity, and our highest frequency, and we see that our minimum skin depth is 500 meters, and our maximum skin depth is 1.6 times 10 to the 5. So when we then want to actually go ahead and design a mesh that we can use for simulating on this, we want to make sure that our smallest cell sizes, so that's what I'm using here for shorthand is CS is cell size, is we've got a few cells that go across that minimum skin depth. So in this case, I want to make sure we've got 4. And then we want to make sure that we've got our region of interest sufficiently meshed. So if we want to look down to 5 kilometers, let's just have a uniform mesh down to there. And then we'll expand beyond that. So we go ahead and run that and see, okay, so our smallest cell size is 125 meters. We want our core region of the mesh to go 5 kilometers. And then in order to make sure that we satisfy our skin depth, we want to go at least 2 skin depths. So we want to get up to there. So what we'll do is actually use those parameters to go ahead and then set up a mesh that does go far enough and satisfies those assumptions. So that's what we do here is we just have a little script or a little while loop that basically says, if I haven't padded far enough, add another padding cell. And then stop once you've hit that threshold that we set of 2 skin depths. So in this case, in order to do that, we went out 25 extra padding cells. So then from there, now that we have all the mesh parameters set, we're actually going to create a mesh object. And so this guy here, we've got our number of cells in the core region. We know what our cell spacing should be. So this is just that padding region, and this is the core region. And then we can go ahead and construct a tensor mesh. And so in this case, I'll show you what I meant by this being an object. So not only it has methods and it has properties. So now that we've created this mesh, there's things that you can do with it, and there's things that we can know about it. So we can ask, how many cells do we have? Okay, so we have 65 cells. We can ask things like, so sorry, when this is coming up, I just did a tab. That's a shortcut in the Jupyter notebook.
So you can type any distance between these cells and ask what's going on?
Yeah.
Pretty cool.
How do you get that window?
This or a new cell?
In 12.
So there's 2 ways you can do it. There's the keyboard shortcuts, which is what I'm using right now. But you can do cell or insert cell above or cell below. And then if you have a look at your keyboard shortcuts, that'll get you going there too. So the mesh has things like its number of cells, but we also now have all of the operators. So if we wanted to look, for instance, at the phase divergence, we have a divergence operator because we've defined all the geometries. So then we just go out and we'll plot the mesh, we'll have a look at it. And so there's sort of 2 things to consider of where we can place things on this mesh. We have nodes and we have cell centers. So that's what we're highlighting here. And because it's just a 1D mesh, it's just a line. All right, so now that we have our mesh, we can go ahead and put our model on the mesh. And so we're going to define a conductivity value at every cell center. So you can think of it as being space filling, as that the conductivity fills up the region between each of those nodes. So it fills up that whole cell. Okay, so here, to make things a little more interesting, we'll add a target. So So we've got a target that's got a resistivity of 10 millimeters. We're going to stick it at a depth of 2 kilometers and make it a kilometer thick. So then to go ahead and actually set up our conductivity model, we start with our half space value with the same number of cells, right? We need a conductivity value at every single cell. We find out where our layer is. So this is just saying I've got my cell centers. Make sure that we're looking above my depth, like in that depth region. We're just going to grab those indices and then stick the target conductivity there. And then to make sure that what we've done actually makes sense, we just want to have a look at it. So we've got our background here. We've got our layer that starts at 2 kilometers depth and goes for a kilometer, and we're back to the half space. Okay. So from the previous notebook, we're just going to import how we solved the MT problem. But what we also want to do right now is go ahead and first compare with an analytic. So we know that there's, for instance, like the propagator matrix solution. So we should, if we're doing a 1D simulation, be able to hit that. So that's what we're going to do here. And so this is just going to compute that analytic. Okay. And so in this case, what we've done is we've plotted the numeric, which is the one that is solving it using a finite difference approach, with the analytic. And we can see we're doing a pretty good job. And one of the things that you might want to look at this point is, so we've got confidence now that our code is doing what it should be doing. We're able to match an analytic and independently develop a solution. But now we can actually go ahead and ask some things like, what happens if we play with our mesh parameters, if we don't have far enough, or if we use cell sizes that are too large? So let's have a look here. Okay, so there's two things that we can go ahead and play with. We can go ahead and play with the domain extent, so how far we're actually padding. And then we can play with our minimum cell sizes. So this is what we set up as sort of our ideal mesh. Now, what do you think will happen if I shrink the domain extent? Where are we going to start to break off of the analytic? Where are we going to fall down?
Edges. Edges?
Sorry?
At the edges?
At the edges. Both edges?
Lower frequency.
At lower frequency?
You shorten the mesh, aren't you?
Yep. And so why do you?
Lower frequencies will have more depth information.
And so the thing that's important to remember too, with when we're setting up a finite difference approach, is what's the assumption that we're making on that bottom boundary?
Background.
Yeah, we're basically assuming that the fields have decayed to 0 by the time we get to that bottom boundary. And so if we pull that up, you can see here we're starting to peel off of our lower frequencies, both in the apparent resistivity and in the phase. Does that make sense? Okay, so if we set that back, and now let's think about our minimum cell size. Where is that going to break down?
When you're at cell size greater than 1,000 meters. If you increase your cell size to 1,000 meters or greater, you won't fit the detail and gravity response anymore, because you can't.
And 1,000 meters because?
That's the thickness of your conductive package.
Okay. I'm sorry? What were you saying?
You skip any piece, right? In the contrary, you don't see it.
All right, so let's go through and see what happens. So you see here, especially in phase, we're starting to break down at higher frequencies. But as you mentioned as well, in our conductive unit, we do see some things moving around a little bit. But it's especially really the higher frequencies that you need to be worried about there.
How did you bring this up?
Oh, the widgets. So this is a package written by the Jupyter group. It's just called IPy widgets. And so all I did is I wrote, this mesh design app is just a function right here that takes the domain extent and the cell size as parameters and builds you a mesh and plots it. And so this is just a function. And then all we do is basically wrap, or like interact a function, and then we give it the 2 input variables. And so I've said my domain should just be a float slider that has a minimum, a maximum, a step, and a starting value. And that just gives you these guys. Yeah. This has been a very valuable tool, not only for courses and things like that, but I know a lot of people in our group are actually starting to amplify their research, which I think is very exciting. Okay. So now what I would like to do is actually have a look at an example of non-uniqueness. And so can anybody tell me the classic example of non-uniqueness in MT? Have a look at the code and see if you can explain it to me from there. If we have a conductive layer.
Conductance.
Can you explain that a little further?
That the difference between thick and low conductance and low conductivity and high conductivity.
Yes, so what we're going to do here is exactly that. We're going to compare five models that have a single conductive layer, each with different thickness, but all preserving the conductivity thickness product. So they all have the same conductivity thickness product. And so this is just setting those up. Here all we're doing is putting those on the mesh. And then we're going to compute some data on those. And then this is just a bunch of plotting code to go ahead and show us what this looks like. So I'll give it a second here. So we've got 5 models with the same conductivity thickness product. And if you have a look at the resulting data, you see that these are pretty similar. In all, we can definitely tell there is a conductive layer, right? We do see that showing up. But the spread between these is pretty small, and you'd be hard pressed to be able to tell the difference between any of these. And in order to really show that, this is clean data, right? And if you actually go out in the field, we of course know that you always have sources of noise. And so even adding a little bit of noise, you really do see that unless you have a priority information coming in, and you know something about these units, you're not going to be able to tell the difference between these 5 with the data alone. And so that's an important thing to remember in the inversion, is that there are multiple models that can fit the data. Any one of these models fits these data. So you can't expect to uniquely resolve any of them without having extra information coming in. Does anybody have questions about this notebook before we move on to the next one?
How many dependencies are required for the screen depths? So, say the longer period, we can calculate screen depths, and then how many the screen depths required for the dependency?
To make sure that you've padded far enough.
Yeah.
So in this example, we use 2, and that's where modeling against an analytic is a good idea, is because you can then actually test and see where you break it down. All right. So here we will move on to the inverse problem.
How do we get to that page?
This one?
Yeah.
So, sorry, I guess I did that pretty slowly, didn't I?
Yeah.
So I think if you hit run.
From where?
So do you have this in your own account at this point? Have you hit clone?
I had mine somewhere, but I haven't got that there. I've got there, I've got there.
Okay. Let's go back. I'll start from GeoSci again. Does that work? So if you go to GeoSci. Yeah. Okay, and then if you go to apps.
That's where I got lost.
Okay, and then do you see simulation notebooks?
Yes.
Okay, so if you click on that, there's this first link that then says Microsoft Azure recommended. So you go there. And then you'll see something that looks a bit like this where your run is grayed out. Is that where you are? So then if you hit clone, that'll give you your own copy. And I'm not going to reclone it because I just did that, but if you hit clone, that should then land you on a page, that looks like this, where you then can run it.
Yeah.
Were you able to?
This hasn't got the.
Would one of you guys who got it up and running be willing to just give him a hand?
Yeah.
Okay. So in this notebook, we're going to go through an inversion, and this is going to use the SimPeg style of inversion. And so one of the things that I'm just going to pull up and we'll probably switch between is a picture of the SimPeg framework. And just to kind of show you a brief overview of how we think about the inverse problem. Okay, so we know that we've got things like our data and uncertainty estimates coming into the inverse problem, along with our governing equations. We know what physics we want to model, and we have some prior knowledge and assumptions. And these are all the things that we want to bring in and actually implement numerically. And so this is the way that we have broken down forward simulations and inverse problems in SimPeg. And each of these boxes is its own object. And so like what I showed you before, it's a module, and then you can build it up, and it has some methods and properties. And this is the same across all the geophysical methods that we've implemented in SimPeg. So we talked about the mesh, and that has your geometry. It also has all the differential operators and all that. When you set up a forward simulation, we break it into two parts. So the survey contains all of the parameters about how you are exciting the system and how you're measuring data. So it's all your geometries there, and then what fields you're listening to. The problem is actually the statement of the physics. So what are we going to solve? Is it frequency domain? Is it time domain? Or is it seismic? So we then need to pair those things. We tell them about each other in order to actually go ahead and solve a forward simulation. So your source gives you the right-hand side. That's how you excite your physics. And then our receivers tell us how we're going to sample the fields and fluxes. When we then go and think about the inverse problem, we're using a classic deterministic inverse problem, where we've got some data misfit, which is a measure of how good we're doing fitting our data. It's often an L2 norm. And we've got a regularization term. And those two are weighted with a trade-off parameter between them. And that's something that you can play with in the inversion. So we combine those things in the statement of an inverse problem, which is an optimization. We want to minimize our objective function subject to potentially some constraints. We plug in an optimization routine that's appropriate for that, and then we can go ahead and solve the inversion. That's the very high-level overview, and we'll walk through that in this notebook here. All right, so we'll get our packages all set up again. So here we given a bit of a write-up on formally how we are thinking about the inverse problem. A lot of this is also in the SimPeg paper and in a tutorial by Doug and Yamawa. And both of those are cited in the MT tutorial, and so you can get them through there. If you have any issues finding any of these things, feel free to send us an email. Okay, so we bring in all of our packages, and now we're going to go ahead and set up a model. So here we're going to use a 5-layer model, and all I've done is define what are the tops of each of the layers and what are their resistivities. So in a lot of ways, this mimics a bit of a typical structure for what you'd think of for a geothermal system. So we've got a resistive overburden, then we've got a conductive cap, and then perhaps a more resistive core, and then some conductive units beneath that. And then here we're defining, again, the same frequency range as what we used in the last example. In this case, we're going to set up our receivers, and our receivers are impedance measurements. So we're going to look at both real and imaginary impedance values. And so this is that survey that I mentioned before. Same as the last notebook, we're going to set up a mesh that is appropriate for the problem. So in this case, this set mesh method, this is something that we wrote for the MT problem that just sets an appropriate mesh based on the heuristics we developed in the last notebook. So that's what that's doing, and then we can go ahead and look at it and make sure that it is actually a reasonable mesh and what we're after. Here, we're setting up the problem. So we have our 1D MT problem. It takes a mesh, and that's because the problem needs to know how to actually solve the physics, right? And because the mesh has all those operators, when you set that up with the problem, we then actually have a physics engine. There's a lot of details on what we've called mappings in SimPeg. We're using a fairly simple one here. And what these are is often you don't actually want to invert for the physical property, like the true physical property. We're not going to invert for conductivity in units of Siemens per meter. We want to invert for log conductivity. There's sort of two reasons for that. If we invert for log conductivity, that ensures that we always get positive values. You can't get a negative value out of that. It also is reflective of actually how conductivity varies. We really do have a logarithmic scale for it. So that's the space in which we want to search for a model. If you were to go to like a 3D here and you want to be simulating in the air, for example, you might want to consider adding like an active cell map. So there's a whole bunch of examples and documentation on how you can use these. In the paper that we wrote, we actually did some interesting stuff with parametric maps as well, as you can decide to parameterize a model in terms of layers or if you've got a block or something like that. So, but this is a fairly straightforward standard inversion approach. Okay, so now that we've got our mesh and we've set up our physics engine, let's set up a model so that we can start to do some simulations. So again, we've got a vector that's the length of our number of cells, and then we're going to just loop over our layers and add those layers to the conductivity value, conductivity model. And then we'll just plot that up. So here I'm plotting on a log-log scale, just for reference. So we have that resistive overburden. We've got a bit of a conductive unit, resistive again, conductive, and then a bit resistive in depth. And so we'll simulate some data over this. And then in this example, we're actually going to add some noise to our data as well. So here we're adding 10% noise to our data. And we can plot that and see what that looks like. So although we're working with impedance data, it's often a lot more intuitive to look at apparent resistivity and phase. So that's what we're going to plot up in all of these examples. So this is the same framework picture that we just walked through. And we've got a few more details in here. What we've done to speed this up, because in this example, we want to be able to run a whole bunch of inversions. So we just wrapped up basically the inversion setup in a little function. So you can go ahead and provide your problem and survey. Here we can provide our starting model, our reference model. Then there's a couple of regularization parameters that need to be considered. So we've got what we're calling alpha S and alpha Z. So our smallness weight and our smoothness weight. And so what these are is in the regularization, we're considering a classic Tikhonov style regularization. So is there anybody who's familiar with what a smallness versus a smoothness term would look like? What is it mathematically or intuitively? Is that about it? No? Like yours? So the regularization is effectively, it's a measure of the quality of our model. It's something that we're imposing, right? We have our data, and that's our ground truth. But that's not enough to actually solve the inverse problem, right? It's not unique. So our regularization is going to help us pick out one model from the infinite number of possibilities. And so a common approach is to use a two norm. Use two norms to set up the model, or to set up the regularization. And so I'm just scrolling out because we've got the statements up here. Okay, so we look at this. Which one is the smallness and which one is the smoothness? What do you think they're doing?
Oh, you guys, I'm gonna cry if somebody doesn't do this. Has anybody been using UBC
Yeah, I
codes?
have, I should know.
Yeah, exactly.
Smoothness is continuing. Green must change from cell to cell, and the smallness is letting that be bigger. It's not kind of, sort of.
Yeah.
I've read this many times. Here I read it.
And there was a hand that came up at the back.
I was gonna say what time.
But only if you drive.
I was just not doing this, but it would make sense that if you want your just numbers in your cells to change smoothly, and then you want to minimize how much change there was between you and I go from 50 to 0 or 1 or something. You'd want to go 50 to 49, 48. That makes sense.
Is the
Is that right?
is the other one, is that the same as blockiness?
Not necessarily.
Smallness and blockiness, is that the same?
Often when people are referring to blockiness, it's actually you're looking at a different norm. And so here, when we're referring to smallness, we're thinking about how small a model is with respect to a reference model. So how close are we to a reference model? And so in this case, this is just basically a two norm on m minus mref. And maybe you've got some weight in there. And then here, what we're looking at is this is basically a differencing operator that does exactly that. You're looking between this cell and the next cell, how much change is there? And let's try and minimize that so that we don't get large jumps. These parameters here then control the relative weight between those two. Is how small do I want my model to be versus how smooth do I want my model to be? So if I make alpha Z huge, what would you expect as an inversion output?
What did you say?
If alpha Z is really large, what sort of character would you expect?
Different values on each side.
Sorry?
They become more dominant than the other one.
Mm-hmm. But what would that cause in terms of the recovered model?
Very smooth.
Mm-hmm. And then if we go the other way?
Be very close to whatever the original reference.
You have a better model maybe, but not that small.
Okay.
Because you have the smaller misfit. I guess at least if you know what's your reference model.
Smaller, okay, so one term to be careful with here is the use of the term misfit. So when we're
sorry, that form and that difference between your model and the reference, the weight of that would be smaller, right? So that might be a better model, like like geologically maybe.
Let's plot it up. Let's have a look. Okay, so we've got those parameters, what they are. What beta is going to do is beta is going to be the weighting between the data misfit and the regularization. Is how much do we trust our regularization versus our data misfit? What do we want to weight? And then there's a couple other things that we have in here that you can play with. Is what do we want to use for starting beta? And then if we want to actually sort of cool beta during the inversion. So start with a high weight on our regularization and say, let's try and get something that's really, really smooth, very well behaved, and slowly progress to something that's fitting our data. So all of that is basically captured in here, and we've tried to comment and explain what each of the steps are doing. So I won't read through it now, but I'll let you guys take a look. Okay. So what we'll do in this example is we're going to start with a reference model, 100 ohm meters. So we'll have a reference model of 100 ohm meters and a starting model that is the same as that reference model. And then here we'll start with our smoothness being a bit larger than our smallness term. And we're going to dive into this a little bit more later on, so hang on to your thoughts about that. And what I want to do in this example is we're going to start with a large beta, and we're just going to slowly cool it and see what happens. And we're going to try and push the inversion pretty hard so that you can see what happens when we do a really good job fitting phi d versus our phi m. So phi d is the data misfit, phi m is our regularization. Zoom up just slightly so it's a 1. So there's a few things that are output by default in a SimPeg inversion, so we can see what iteration we're on. What beta we're at, what our data misfit is, and what our regularization is. And then this is the objective function value. So this is phi d plus beta phi m, so in this case they're the same. So we're going to run it for a maximum of 35 iterations. So I just told this inversion stop at 35 iterations. So what can you tell me about when you actually want to stop an inversion? What's a good choice of beta? So how well do you want to fit phi d versus phi m? What kind of things should factor into that?
How good your original model was. Your misfits, what you produce is what you put in.
Well, what do you mean by, I guess, how good is your...
Or how constrained it was to the human, like whether you had a borehole or whether you're just going from,
How confident you were in your original model.
Okay, so you're focusing there on the regularization here.
Okay.
What would you expect about your data misfit here?
It depends on your error levels. For beta, is this like, is that the same as what they call a tau factor or tau factor? Is that the same thing? The tau. Tau?
Where does...
Is that the same?
Tau goes, I think more, is that the Bayesian notation or something? I'm not really very familiar with tau.
Does it do the same job?
I'm not too sure.
Trade-off parameter for different inversion. Yes, but does it do?
Yeah, I think you're right, Sasha.
Yeah.
You decrease, relax tau later in the iterations to relax your regularization.
Okay. Well, yeah. So if it is the parameter that's between, if it's phi d plus, and here we're using beta phi m. If that's tau. So I guess perhaps the most important thing to think about when deciding when to stop an inversion. What's the thing that you trust the most in this? What is your ground truth? Exactly. So that's what we should be making decisions on. And so that means that we need to be focused in on the phi d term. So now that we know that, what should be your stopping? What's an example of a stopping criteria?
System noise.
System noise. Okay, how do you bring that in?
I guess you know what the system noise is for the receiver that you're using. So do you stop it at a percentage of what that noise is, or?
Effectively. So what we typically do is we're going to weight each datum by how noisy we think it is. And then if you have set up if you've done the correct weighting on all of your data, so that's what that WD matrix did when we did D minus D all times WD. So if you've done that correctly, and your noise is Gaussian, and we're using a 2 norm, then you would expect that basically we stop when phi d is the same as your number of data. So statistically, that's a good target estimate. And so in this case, that's what this star is plotting. So here what we've plotted is our phi d versus beta and our phi m versus beta. So can somebody explain to me why phi d increases when we are increasing beta? And maybe why phi m decreases?
You putting more emphasis on phi m when you increase beta.
Exactly.
So
exactly. Does that make sense to everyone? Oh, okay. So what she said there is when we increase the beta, what we're doing is putting more emphasis on fitting phi m, and we're caring less about phi d. And so in that case, what you do is we decrease then phi m. The inversion will do a good job fitting phi m and not so much on phi d. Whereas if we decrease beta, it goes the other way. Okay, so perhaps most interesting is let's actually go ahead and look at the results. So this is just a whole bunch of plotting code to make the plots look nice. It looks like a lot of code, but that's all it's doing. So we started off the inversion. What I'm going to do is scroll through each iteration. And so we started off the inversion with our initial model, which is the same as our reference model. And so what do you think is going to happen if I go, so you see that here, sorry, I'll ask this question in a second. So you see that here, as we go to smaller beta, as we decrease beta, we're starting to introduce a bit more structure. So we're starting to see a bit of conductivity coming in. And as we keep going a little further, getting closer to our target misfit, we're doing a better job introducing structure here. So we do start to see, there are 5 layers here. And so here, I think it was 8. 8 is when we're hitting our target misfit. So in this example, we do see that we have our resistive unit, and we are resolving 2 conductive layers and that basement. And so then they are smoothed out. We've asked for a smooth model in our regularization, and so that is what we're getting. Now, what do you think, what do you expect to happen if I start increasing and continue pushing the inversion? If we're trying to get out here, what do you expect to happen?
more structure.
Okay.
That's your artificial.
Yeah, so let's bring it way out.
Lindsay, do you give me now bronze or silver?
It's up to Doug.
He was generous. Gold yesterday. Come on.
Give gold stars away, like candy. So exactly, right? We get a whole bunch of structure that's trying to come in to really exactly fit these data. And so this is an example of overfitting. We're fitting into the noise. And so the inversion we can get a result. I mean, we are fitting the data, but this model is not making sense. And so here, all we're doing is plotting an example of the model where we're hitting the target misfit, so that's the blue one. An example where we're overfitting, so we really do see that there's a lot of artificial structure coming in. It's dangerous to see that we've got another layer that came in here. And then the underfit example, we show, there are 5 layers, but we can get more out of the inversion still at that stage. Okay, so now coming back to one of the original questions about the regularization parameters. So here what we're going to do is we're going to run a smooth inversion, and we're going to run a small inversion. So in one case, we're going to have the smooth inversion is going to have a larger alpha set. So we're really turning down the volume on that smallness term. We're saying, give us a smooth model. And then we do the reverse in the other one. And so which model is going to have more structure?
Smoothness? Smaller?
You're really hedging your bets. If you're right, you get a half a star.
So we'll run both inversions till we hit that target misfit. So we're going to try and do an equal job of fitting the data. So in this case, we're not going to be overfitting the data. We're going to fit the data the same, but now we're changing the regularization. Okay, so we ran the smooth one, we fit the data. We've run the small one, we're going to fit the data. All right. So can you explain what's going on there? So in the small model, because we really asked it to try and fit the reference model, which is 10 to the negative 2, it's going to try its best to put values there. And it's going to try to sort of minimize how many other values are away from that, right? And so in this case, it's much easier to introduce more structure and keep most of the values right around our reference model. And so we do go ahead and introduce this extra spiky structure because we have not asked for a smooth model. So that's one thing to be aware of when you really are trying to hit a reference model or something like that. Is it's a good place to introduce some a priori information, but in this case it can be dangerous because you can introduce some extra structure that is not actually there. Other questions, comments?
How you trust the pinpoint, the techno point? You use that as Jack method? You plot the techno curve. Some people suggest that the turn point is like that point. What is your experience with that?
Yeah, I mean, it's a matter of looking through the inversion results and comparing both. And so that's why I think examples like where you can actually go and scroll through and see all of those models, that does help you define where you should be stopping the inversion.
Yeah, I found we tried that approach. I found sometimes it works, sometimes not. This is why.
I tend to overfit and then I go back and pick the model back.
Well, it's
too noisy and they come up with a mesh sort of come through, obviously too far.
Yeah, and it's helpful to be able to run an inversion past what you would consider to be your stopping criteria, is to really see what is it trying to do.
Particularly run it overnight, not there. I'd rather run it too far than too short.
Yeah.
So back to that discussion we had with Janelle, everyone was saying what to put in the model. So you're saying it's not good sometimes maybe she would put those layers at the project if it would be the reference model and she would introduce something, wouldn't maybe work this way, right?
No, I mean, a reference model is a good way to introduce some a priori information. If you do know that those layers are there, you're not necessarily harming yourself by putting that. But it's important to remember you don't necessarily want to sacrifice things like smoothness and try and put all of your weight onto a reference model.
Right, I see. So how do you know then? You run 5,000 of inversions and figure it out what is the problem?
Well, you've got lots of parameters to play with. I mean, in this case here, if you can see that things are coming down to your reference model at the back end, so you know that you're really not seeing, you're likely not seeing that deep. And then you might be suspicious because you put a high weight on trying to make things as close as possible to 100 or to 0.01. Seems for me here that, okay, maybe I don't really have the right background model. And maybe that's what's causing those spikes. So at that point, you might say, well, let's even forget about having a smallness term. I mean, this could be run without a smallness term. And then you're just basically looking for something smooth, and then you get this blue one. So just those two models actually tell you a lot. You don't really need to run 5,000. And Ron's comment, I think, is 100% right, which is generally what we do. We just kind of run this thing through, and you're probably overfitting the data, so you've got lots of structure, but you cannot rely on the program or any algorithm to tell you which one to choose. Ultimately, this has to be a decision that's made by you on the basis of whatever information you've got. So you look at something, it looks really like it's got a lot of structure, you maybe back it off a little bit, and then find something that's geologically a little bit more appealing to you. If you're still fitting the data reasonably well, so if you're still kind of within a ballpark of what you think you should be for an overall misfit, that actually maybe is as good a model as you can get out without doing something that's extra good.
But I also do, I guess, the cluster calculated the curve and plotted and emails me that, so I can see after each iteration how far it goes. I can get it to stop it, or
yeah. That Tikhonov curve is got a huge amount of information. Do you have it? Yeah, there we go.
I mean, because you can see examples where we can see here we're still making a lot of progress fitting the data.
That's how we flatten it out.
Yeah.
You tend to be terrorists in America case and drop down, they flatten and drop.
Right. So whether you're at the star or whether you're here or whether you're here, those might start to be pretty subjective decisions. But as Lindsay said, here you definitely know, like, okay, I'm getting much more reduced misfit. And then if you look for your, I guess we don't have the model objective value, but if you looked at your model norm down here, it would still be not increasing very much. But then, as you're turning the corner, well, sure, your model starts to increase a lot as you go down here. So you don't really have very much incremental change in the misfit. So here you're getting the big bang for your buck as far as not very much change in your overall structure compared to a big decrease in your misfit. Whereas here, you're just putting in much more structure. You're not really decreasing that misfit. So you want to be not on the right-hand side. You want to be not on the left-hand side. So you want to be someplace in the middle. And some people use L curve. Some people just try to do what they expected misfit would be. But you're really at that point, you have to have a little bit of subject to go for that.
So I'm interested where the star is. Do you ever plot the overall cost function value?
Yeah, so we certainly can.
There we go.
Because I noticed the overall cost function value was decreasing, and then it increased slightly longer.
Yeah, let me see if it's in. sorry, live coding.
And you're talking about plotting the overall cost function. The other thing that's interesting to plot, you've got a model objective function regularization function. It's got a couple of terms. It's got a smallest term, it's got a smoothest term. You can actually look at those individually and try to kind of get a balance of, just how much, for a particular data, but how much each of those is contributing. And that sometimes is insightful.
Let me just reverse the axes here. So in this case, you can think about it going the other way. Sorry, it's a little confusing because we started at high beta and then decreased it. So we start up here and we're decreasing our cost function. So it does wander around a little bit, but we still are overall decreasing.
Yeah.
And I just wanted to follow up on one thing that Doug was saying here too is, I mean, if you look at the models that really are right around your target misfit, this is where some subjectivity does come in. And if you have information that supports, a conductivity value, if you've got a well log here and you're hitting this conductivity value, maybe you prefer this model. So it is something that is worth looking into and factoring in information when you are deciding which model to pick. So the last thing that I wanted to show here is just that we did, I did try and set up your example from this morning. And so this is now plugged in, and you can go ahead and play with some of these inversion parameters and actually see what's happening and see what you might expect when you're doing a small versus smooth inversion in this case, or what the impact of your reference model is, what the impact of your starting model is, and see what choices matter there. So here, these might not be quite right, I just picked them off the screen. But the layer tops and the resistivity to the layers. So we follow the same game as last time around. And I'm blowing through this pretty quickly because we walked through it before. So this is what it's looking like roughly in terms of conductivity. And here, I didn't remember what your frequency range was, but I've used the same as before, so 10 to the -3 to 100 hertz.
Yeah, so this would be 10,000 hertz to
10,000.
Probably 10 hertz.
Okay, so higher. Cool. So we can do that. Started. Yeah, so we can take a look at what you expect to see for data there, and then go ahead and start playing with inversion. So in this case, I haven't played around with these parameters with this high of conductivity yet, so we'll see what happens.
So what's the skip BFGS comment about?
So in this case, we're skipping refactoring in the optimization. It's just a piece of optimization. So this one's line switching. So this is roll down for. Let me just go back to the conductivity range I had before. And so with SimPeg, these are 1D inversions that we're playing around with. If you actually want to go in and set up things that are larger scale in 3D, There is machinery to do that. It's still sort of at a more research level, like bringing in and inverting a large data sets. We're not there yet, but certainly open to contributions. And if there are people who are interested in making that happen, please do get in touch. There's a lot of people who are actively working on this and trying to continue improving.
So what is it? Can we take our problem, go there and get free data, free software to use?
Yes, so SimPeg is available on GitHub. It is completely free. So you'll have to do the work to get your data in there. We don't really have parsers and things like that set up. But in terms of getting going, there are a handful of examples that are pretty good. And then, as I mentioned, that Google group is a great place to get in touch. Sort of once you've played around with a few things and you know what you want to do, there's a lot of people who can help out there.
So, following up on the data parts of problems, all of this so far has been dealing with synthetic data generated from models.
Yep.
So is there some information in the documents about how to parse in real world data?
Yeah, and there's a couple examples, and I know that Goody has some examples of getting actually data that's in an EDI file and all of that. So.
But if we come back to the problem that you were talking about when you were doing the conversions, an important thing to know with any inverse program is what that regularization function is. Because just as Lindsay showed you, even in this one, you have a couple of parameters and you can greatly change the result. So the regularization function is actually the horse that's pulling the cart in these things. It is it is arguably the most important thing from the point of view of getting out something that's useful. It's where you're putting your a priori information. So your a priori information may not be very much, but maybe it's half space, but maybe it's more stuff like that. So all of that work that goes into building up the reference models and stuff, and then what you think you know and how you want to tailor the regularization function, that should all be done like at the beginning when you're really thinking about what you're trying to get out. And then what do I have constraints? Well, I've got well-log constraints. Oh, I've got some data. I've got some geophysical data. So you can actually think about the most important part of this inverse problem being driven by what your form of this regularization function is. So it's really important to know. And then, of course, then you want to bring in the data. You want to make sure you want to fit the data. Don't underestimate the power of regularization.
Yes. Yeah, so this is one example, very quick, but I think it'd be an interesting place to start jumping in and playing around with things. So here, start this setup of your reference model, of your initial model. What are those alphas? What's your beta? How are you cooling that? All those kinds of things.
And the other major item here in the Achilles heel is the definition of your misfit function, which even in L2 still requires some kind of scaling by the uncertainty of the data, which is not a trivial thing to do. And it's problem by problem dependent, but usually kind of thinking the floor and percentage is the first guess through, and then working with that. But those are the two things that really determine the quality of the output. What is my definition for my misfit and the numbers that are going in? What's my definition for my regularization function, and what are the numbers that are going in? And that can require a lot of time. To get that right, then you have a good chance of getting something good.
Yeah, so a few resources to play with, and this is all posted and now a part of the simulation notebooks that's on Azure. And so if you run into any issues with them, please get in touch. We're hopefully going to continue adding to these. And so if you have an idea of something that you want to try, that's actually a very exciting place to contribute, is having people build up examples. And so please get in touch if that's something you're interested in doing. Any other questions, things that you'd like to see, go over, or be toast?
Only implemented in Python 3.
It'll run in Python 2 or Python 3. We're trying to move and promote people going to Python 3, but yeah, it'll still work in Python 2.
Okay, cool.
So where are we with respect to who operates wish lists?
So if you go to, we put this wish list up, tinyurl.com/this wish list. It'll bring you here. And so, do you want to explain?
Well, the goal here is just to try to extract from everybody, one thing that they would like to see. Right? So if you can sign on here, put something on that like, oh gosh, if I had this, that would really make my life easier. And
What was the address again?
It's tinyurl.com/disk wish list, all lowercase.
so I think each person could try to think of one thing that would increase the quality of their life and help them out through their problems. If you have more, that's fine. Actually, you have a long way.
He loves the
Okay, then I think we're pretty much wrapped up here. So I hope everybody has found this useful. I really want to thank everybody for having done the presentations today. I thought there was some really interesting stuff going on here. And it's nice to kind of get a feeling for what that is and to have it captured. It's great. With that, I want to say that the Brisbane audience has been the best that we've had in Australia. So I think we're good to go. We give out more.
More gold stars.
Now, we did say when we came to Perth that they were the best audience that we've had in Australia so far.
Good recovery.
Anyway, you guys have been great. So yeah, thank everybody, and yeah, we'll see you maybe at an ASCG or something.
Can I just can everyone join me in thanking God?
This is so much better than Hathaway.
We didn't say that person was the best.
Yeah. Well, they were. No. That was quite fun. Oh, how nice. So yeah, so I was Josh in Adelaide. Well, traditionally the ASCG gives out a bottle of wine, right, to guest speakers. And so he said, yeah, do you like Shiraz, or what kind of wine do you like? So I wrote him back and I said, well, both Lindsay and I really enjoy Shiraz. And I thought, okay, that should be pretty clear. Like, okay, there's two presenters. We both like Shiraz. Maybe we get 2 bottles of wine. Nah, you got me 1 bottle. Sure. Anyway, thanks.
It's actually a Queensland tradition to hand out a book. So you're lucky I talked to Hank into wine.
Oh, yeah.
She gets another gold stuff.
So the ASCG has a book.
So it's just different from state branch to state branch, and we usually, Hank usually hands out a book called The Main Inheritance, which is a.
No, I got that book.
Yeah.
You would have got it. But speaking of books, this is kind of interesting, right? Because the guest, as done by the SEG each year, has a book where the guy gives whatever the discourse is, actually has a book. And that's a huge amount of work. So the SEG said, okay, you're going to have a book? And I said, no way, right? First of all, it's a lot of work. But second, and even worse, by the time you finish it, you press the print button, it's out of date. So we decided, look, we're going to go live, hence the open resources. And yeah, so there's no book from your end, no book from our end, so we're good deal. And we have 2 bottles of wine, we're good to go.
Like, I have a question.
Yeah, so this is actually around,
No,
this is actually X. It's just markdown. So if you want to like steal the latex.
Oh, yeah. That's pretty. Yeah, you can actually kind of make a translation of those length scales to the alphas. I think in the code it would come out as an equivalent alpha. Like, you know, I think the output file or something yeah. And then you can check, you can see like, okay, maybe that looks a little bit big.
Yeah. But everything keeps in your hands. It's so easy for an to get black box. Yeah, that's the goal. Yeah. So that was small next yes.
But you know, those are things.
So typically when
I
was talking about goodness, I would
kind of go back and just see what's
and then
Would
it has
it be a different results by having using the other terms, the 3 plus 1 instead of any Z?
Yeah, that's pretty cool.
But are these more effective?
Well, there's an equivalence, right? So if you use the length scales, then that kind of translates back into an alpha, you know. And
Is it 1 to 1?
oh, I can't remember exactly how the formula goes, but it's.
No, but is it sort of equivalent, fully equivalent?
Yeah.
The results about saying Z. Do I get the same flexibility?
Sure. Yeah, so you could then go to alpha.
So smallness is just looking at every cell on its
X, Y, and Z. Yes, there's square root.
5 minutes later,
If you have a length scale of 1 to 4, then I think the alpha S goes 1 to 16.
Yeah. So what
Or
the
maybe 1 to
smallness
2. I'm not sure, but
basically
it's
has no knowledge of its nature. All we're doing is looking at this cell and saying, how close am I to right?
yeah, I mean, sometimes once
Yes,
you've kind of got things
Going
going and everything is more or less the same.
And so all we're doing is
do
measuring
this
how
data
far
set,
are we
that
from
you don't
our.
have to change things.
And that's all that does. So it doesn't care, like it doesn't care if there's a big jump between itself and the next one. So it's essentially sorry, when you're running an optimum, it's like that. It's like when you run an optimum, it decreases the biscuit as it drives it harder and harder.
Oh, yeah.
Sounds like it'd be a fun day.
Yeah, and then you can take a look.
That's how it looks. Yeah. Right, but are they changing alphas?
This is what I used to do for experiments.
Oh, yeah.
Okay, yeah, because I mean, typically I would measure, like I would choose my alphas, hang out around that rest of the version. The beta is really easy to change.
Oh, you done this.
Yeah, and so there's a bit of that. So yeah, so when you mix up so in this case, I'm just trying to think through what I put in for the end. So there's two things that we can do, is we can actually do a fixed intervention, or what we've done here, and
Exactly.
we often do this in an inversion, and use beta estimates.
Yeah.
And so what that does is it does actually estimate your first beta.
It's been a long trip.
Yeah, and so we actually did do that. I didn't want to go into the details of it, but we did actually estimate the first beta. So all you do to do that is we basically look at our phi d and our phi m, and we try and sort of guess like how big are they relative to the control. And so we say, okay, if phi d is on the order of 10 to the 5, and phi m is on the order of 10 to the 3, like let's try and bump up beta like to be 100, so that they're kind of equal. And then here's what we did, because I said, actually I want phi m to be even bigger. So I figured out like what beta's gonna be, and maybe it's 100. And I said, okay, let's make it 10. sometimes bigger, and so we bump up beta and then gradually decrease. So there is you know what, we totally do have an example. It's a little buried. So if you send me an email, I can dig it up for you. Yeah,
Yeah, I think we're probably
so. Yeah, for sure. I don't actually have a card, but I can give you my email. Or yeah, my cards around that. That would be great. Some people actually. Anyway, thank you very much. Yeah. That would be awesome. No, it doesn't. So that's, yeah, so if you're using, so there's a citation for Rowan's paper, which is calculated all data 15, and they're using EM, just came out, it's and I'm happy to email you those if you want to. Yeah, I mean, that would be great. Yeah. But no, it is huge because, you know, software, it's a ton of effort to actually get it set up. But yeah, I mean, that would be awesome. And if you're deploying your software, maybe a few more resources on, like if you want to share code and stuff like that, on how to get DOIs, like I've used BigShare to actually publish an example where you keep where the code gets a DOI, which is super handy. So yeah.
Thanks for the time. And I just had to keep your ear out in case I need to.
Yeah, for sure. Please do get in touch.
Yes, code.
You have to probably use it as a
UBC.
Okay. Yeah, exactly. Yeah, but feel free. I mean, it's always useful to get perspectives from what are you using. Yeah, and that's such a great place. We're always in need of examples.
Thank you.
Yeah, perfect.
That's
I guess my job is I'll help you look at your sample with the higher frequencies. So just use the yeah, but it wasn't.
Yeah,
it wasn't all that.
processing data.
Yeah, for sure. I'll play around and see if I can do parameters a little bit, because I started just like fun enough without thinking too much.
Different frequencies,
yeah, absolutely.
already large and this was we don't want the data you know what
My response is so one of the things that we do, and I glossed it when I didn't actually start but one of the things that you can do is actually choose data based on basically how big the ID so since we're looking at the ID and then choose a beta that says, okay, I want my FIM to start out 100 times more important than my FIM, or 10 times more important than my FIM.
so whether the data is changing during
You know what I mean? So okay, so that means for the data estimate, that gives you a starting right? And then you're also thinking about the so typically I wouldn't actually recommend this one where you're cooling data every other day, especially what I would yeah. So I mean, and it takes a bit of playing around and getting to know your problems. But I would typically take a few steps at a single beta. So choose a beta and maybe try and do 4 iterations of that beta. And then we'll cool beta by a factor of 4. And then do 4 more. But it's integrated.
So very large data several iterations, it will decrease slowly after several iterations. Because data is still very large, though it's put together, but it's still large. If you choose a very small data, you can't get good results because you always have to fit the data. So the large value of the starting with beta boosts just depends on the or just the highest sample beta.
So I would often choose a beta that's going to several factors. It's going to make my regularization a couple, maybe an order of magnitude larger than my database. Order of magnitude. You want to, especially if it's a highly unstable. And so your regularization basically gives you a locally linear problem. And so it's important to start with high regularization so that you really guide it to otherwise it's very easy to get dropped in someplace. And so if you can start with beta. Exactly. Yeah. So I would start like so here in this example, there's this particular chain like where you estimate the eigen values of your regularization and so that basically tells you how big you actually versus my regularization. So your data management is looking at potentially magnetic field measurements, right? And your regularization is looking at something that is units of log connectivity. So they're completely different. And so what we want to do is get an estimate of, okay, do I expect my phi d to be maybe 10 to the 3 and my phi m to be 10 to the 5? And this was like, or maybe it's the other way around. Maybe phi d is 10 to the 5 and phi m is 10 to the 3. So maybe my first data should be about 100 to balance how well it's
how do you judge whether your phi d should be 5 versus 5 or 5 give this standard
So what I would typically do if you're starting out with very little sort of a priori information, you're getting to know your data, I would start with a big beta.
What I want is actually finding small alpha and also small beta counting function is very small.
Yeah, yeah.
That's what I want.
Yeah, absolutely.
Yes.
So I would typically like start with perhaps a higher beta than what you even think. And then push down, and then once you sort of are like you run an inversion, you're never just gonna run one inversion. That's not going to be a public answer, right? So what those models are doing out there. And then perhaps run the lower one. See, you know, the so maybe you can actually start at a slightly lower beta. It just depends on how much requirements. Like if you've got some significant structure that it's quite an involved data set.
National use high beta, maybe 3D small beta. So I guess whether I use just a small area to test the data cooling schedule.
Yeah, the survey's
maybe this value is too high or this value is too small.
Yeah,
I use this.
it was very nice to meet you. Yeah, you too. And hopefully we'll be in touch. Yeah,
That would be great.
Yeah.
Oh my God, see ya on the phone picking.
Yeah, so like what I would try to do in that case is come up with a simplified 3D model that is a bit in a smaller domain that you can work with. Yeah, like pick something representative that's complex enough that you can get a feel for how the versions are. These are great because they really do run in real time. There's a couple other linear inversion examples that we have that, I mean, they run in real time. You can get a handle on like what is your small numbers.
So now I can find out that. And we so
all that
and
was
around
tutorial from 2005.
We'll see that.
I think that's very
So then I go down to
it's a good paper.
Access to it.
Not an error.
It is a paper. We cited in our synthetic paper.
So I just get like it's tiny little thing. So I mean,
If you're little link in here, if you have to shoot me, it's on. It's for sure on the GIF website.
It's just basically
add on their own way of bringing the data in.
Yeah, I think so. And I think that's a great thing, because then you get other input and other ideas and things like that coming in. So
it's sort of like a whole new sort of paradigm.
It's being
It's just like in the 80s and 90s that technology and all that sort of stuff and versions of stuff that come in, but now it's like it's really about solving these problems rather than worrying about all those sort of the shoulders of giants.
Yeah, it's exciting. I mean, because all of these problems are really small, right? Like people know how to simulate 3D MT. Like, it's not, you're not going to get a PhD at that, but you need access to all the knobs to actually answer your PhD question.
People around the world, which are listening, so fast levels and
oh yeah, they did, and then
and that's what we're hoping to do. It's still definitely early stages, but I mean, if we can get people on board and involved, I think it has a lot of potential to, I don't know, be a bit of a home for solving some of these problems and working together on stuff. Because there's no sense in like writing all the material.
have basically to do all of this. Exactly what my project is.
Asking how I can sort of help see that process.
And it's one of those, it's like, how does
Yeah, that is
Yeah, okay, so there's
we don't want to.
there's a number of packages that we have. But specifically, there is actually a process.
Sometimes.
And so right now, there's not actually a bunch of this. I wouldn't actually even bother looking at the code because it is just scraps at this point. What I would look at and love to hear your thoughts on is any issues. So we've tried to just start sketching out what this package should look like. What references should we be looking at, and how do you want to interact with it? Sort of laying as much groundwork as we can before actually doing anything. And then we've got. Yeah, so here, like if you look at the scope and the description and you want to write out a comment, as long as you have a GitHub account, which is free.
There's still.
Yeah, it would be great to get your.
We're going to talk about it anyway.
You mentioned before that simple.
Yeah.
So in your simple, is there showing?
So it's about
But then I got an email the other day saying you could on the ACG.
We don't have one right now live, a EDI file. Guni has some. If you email us through the Simpeg Google form, I'll get you in touch with him.
Because
yeah.
I got an email.
I don't have experience of the.
I was under the impression.
Yeah. I'm wondering what's the process of doing.
I just got an email just going, oh, you're in the team.
Yeah, so Guni's got a couple examples of that. We don't have many live on the web, but if you get in touch, I think we can lead you to some things. GUDNI. But if you ping through the Google form and yeah,
Maybe they're planning.
Yeah.
It didn't look like it was.
Is there a
There's going to be.
screen spreading out when like you
we don't necessarily, we don't have an example of that, but I can, like, we have examples where we save data to standard files.
I'll roll in
Have a look through, so there's a few examples. So if you go to the docs, there's a whole bunch of examples here. And so there's a couple frequency domain analytics. This one is an example where we're inverting real data. It's not MT obviously, but it can give you a bit of an idea of what that looks like.
my phone number.
There's a few examples of natural source MT and stuff in here, and then there's those MT tickets. So with all of that, this should sort of get you up and running. Because dealing with input and output, that's really mechanics, right? It's important, but it's sort of not the heart of the problem. And so if you play around with those examples, you'll get at the heart of the problem, and then figure out if it's worth it for you to actually get your real data. Yeah, nice to meet you too. Very nice to meet you. Okay. And then especially if you're working on early life.
Sorry, I got the
I tried with one